Um, yeah, hi. I just wanted to hear in the chat box, you can just type what you feel is process safety. I mean, you can keep giving answers so that we can make it interactive a little bit in the first instance, and then let us later on take it forward. Just people can. Is chat box visible for everybody?
Yes, sir. Chat box is visible for everybody. They can see what they want. Sir, we can unmute also. If, like people are raising hands now, so one by one we can unmute for some participants only.
Yeah.
That would be also better.
Yeah.
So you want me to unmute or chat box is fine?
Chat box, as of now, chat box is fine. So
Okay.
evaluation of process hazards to prevent containment failure all along the processes. Yeah. So understanding the health of the process is wonderful. So process safety is the discipline of preventing, managing catastrophic incidents involving hazardous materials or energy industrial process. Oh, good. Wonderful. Prevention or loss of containment, practice of preventing fires. Yeah. So I think wonderful. I think a lot of people are giving answers. Wonderful. Yeah, this is. I think Jagannath is saying hi, Satya. Yeah. Hi, Mr. Jagannath. How are you? I know him pretty well. I know quite a few people here. So world is small. Okay, it is DNA. It says of safety management. Yeah, good. So analyze hazards and take preventive and protective actions to ensure safe design. Okay, wonderful. Okay, so good. I think people have definitely have got a lot of clarity. But what exactly happens is, when people are trying to, one of the biggest problems which people face is how to separate process safety and process safety management or anything related to process safety X. So something, if at all they say something beyond process safety, people actually have confusion. So we will try to dispel some doubts as we move along, and the whole session is about understanding hazards, understanding, some person talked about like getting into the process, getting in and knowing about the health of the process. I think, yeah, few statements are pretty good. I mean, so people have given the answer. So when we're talking about process safety, as many of you guys have mentioned, it's about like definitely looking into the health of the process, looking into the processes or operations which you're managing, getting clarity about the materials you're handling and how the materials behave inside your processes or operations, and what is actually going to happen when you ultimately take these materials and handle them on a commercial operating facility, and how you got to manage to make sure that you don't have any kind of incidents or any kinds of accidents thereon. So this is about like overall about process safety. So, but how we in fact can get clarity on, or how we can have information about whole of the process or um, the whole of the chemistry that you're handling, how to get into the details, how to know. The real problem is many a times, I mean, I'm telling you, as we talk about some case studies, we will come to know many a time problems have happened because people were ignorant. People were not clear what was really happening. So nobody wants accidents to happen. Nobody wants incidents to happen. People want things to be safe at their end. I mean, when you are spending millions and millions of dollars to construct facilities, plants, obviously you want to run them safely. And so there are so many people who are involved, to make sure that, the whole of the process runs safely. So business is one thing. and ultimately you want to get a good quality product and you want to sell the product. And so whether it is a product which you manufacture as per the customer's requirements, or innovative products which you make and release in the market, in whatever way, whatever kinds of products you make, ultimately when you take or manufacture the product through a series of steps, you definitely want to have clarity on the process as we move forward, and as we are going into further, as we go into further into the future, people want more and more clarity. And so it is not just about the chemistry, it is in toto about everything about the process. So earlier was the case wherein people were interested about chemistry, people were interested about only design, people were interested only in the chemical kinetics, or people were interested in about how the chemistry behaves. But on the safety grounds, is it really required? I mean, people were in fact missing out on. So today's agenda is going to be like, introduction to process safety. Then we will talk about how, what are the steps we need to take. So in order to, in fact, process safety, in fact, anyway we decide, we eventually don't want to have any kind of instance of accidents or any kinds of situations wherein, we create trouble to the people, our environment, or the world at large. So for that, how we can go about, what sort of clarity we need to get into, how we can in fact understand, as somebody was mentioning, health of the process, how we can know about the process itself. So for that, we got to take stepwise approach. So as a part of this stepwise approach, first of all, we'll try to understand in what way we can screen the process. So whether the process itself is, safe or not. Then once we screen the process and once we found that the processes are reasonably safe at the screening stage, we'll try to understand the process exactly as they are happening. I mean, we really want to know what happens to the process itself. So when we go from a laboratory to a pilot plant to a commercial operating facility, this data is going to be useful for us to make sure that later on a commercial operating facility, we don't have any kinds of issues. So it is about understanding the process as such, the way you are operating. That is something we do later on. And then we'll try to focus on certain reactions because, various kinds of hazardous reactions are prevailing. We'll try to get into, so initially I'll talk about few case studies, but later on we'll try to talk about various hazardous reactions, which are very, very critical, which people keep handling, but really are not aware. Then we will try to understand about runaway scenarios. Suppose you are managing your processes very well, wonderful, but because of some reasons, your processes might run away. In the sense, you'll reach certain situations wherein you will not be able to control your process. Those are called runaway scenarios. So, is there any way, or is there any possibility that your reaction could run away from you, or you are not able to control? Those kinds of situations also might actually arise. So you've got to understand them. Then we will talk about integrated process safety, and we'll talk about guidelines for process safety design. I will definitely have to talk about static electricity and powder safety also in this presentation. So it's going to be post-lunch for a couple of hours, because it's also very, very important. So when we are talking about reactive hazards and we're talking about thermal hazards, we definitely need to talk about hazards due to static electricity and also dust explosions or powder safety. Then we will close the session, and I want to actually hear from you also. What are your expectations, or what are the range of expectations your organizations have, or your own, if at all you're running your own companies, how do you want to run your companies, or in what way, in fact, you want to look at the process safety? Maybe we can discuss in general. If we definitely have time, we can actually have one breakout, the group session, and then discuss as well. Okay, this is the whole of the agenda. So as I keep sharing the screen, what happens is that I'll keep moving forward. So any of the questions you have, queries we will take during the break. So around 11:15, we will be taking a break. So at that time, we can, in fact, so it's going to be a 15-minute break, tea break. So during that time, we can discuss. Shalini, in case
Yes, sir.
in case you feel like you need to interrupt me, you can interrupt me anytime. So in case there is something very important to discuss.
Okay, sir. Okay.
Okay. So then what I'll do is I'll start sharing. Yeah.
Yes, sir.
Shalini, you want to talk anything about emergency preparedness, or shall I go to the presentation?
Presentation, we can go.
Yeah. So again, the definition, as just listened, this is the ASCHE definition, American Institute of Chemical Engineers, which they say a discipline framework for managing the integrity of operating systems and processes handling hazardous substances by applying good design principles, engineering and operating practices. So process safety entirely focuses on reducing the risks which are associated with processes handling hazardous materials. So these and the efforts are to reduce the frequency and consequences also of potential incidents. So these include toxic or flammable material losses resulting in toxic effects, fires, or explosions. So the incident impact includes harm to people, harm to facilities, harm to environment, property damage, and also, I would say, as I told, the world at large. So when we talk about process safety, I just keep on actually telling. So the chemicals, materials, and equipment, they are a part of your process. So you have chemicals or materials which, in fact, you bring in contact with each other. You bring them in an equipment where you manage your process. So when the reaction happens or when the interaction happens, you try to understand what is actually happening. And then later on, this whole of the stuff happens inside a vessel, which is an equipment. So you just try to get to know about the equipment in which you are handling. Then, based on the data you get, you design your processes and then engineer your processes for safety. So once you have relevant data, you develop operating procedures based on the developmental studies you do and also the safety information you have. And then you take it forward. And so these top three essentially become part of your process safety. And in case you are applying management controls to make sure that you eliminate incidents, because an industry is involving multiple people. And so if management also comes into play and then make sure that they create systems such a way that the process safety incidents don't occur, the whole thing becomes process safety management. So this is what it is. So the top three elements essentially are part of process safety, and once you bring in the management, it becomes process safety management. So quickly, I will give a difference, because this is something which you got to know at the start of the session. Because process safety management is a concept which got originated from Occupational Safety and Hazard Administration of United States of America. This is because of a lot of incidents which have been happening in various industries across, but they realize that people have realized that it is not just it's not having the awareness. It's the people also who need to have awareness, and there has to be systems actually, or the management has to come into play. So there has to be a top-down approach wherein the management also plays a role to make sure that the incidents don't occur. So that's how the process safety management concepts have come into play, and it has been proven beyond doubt that once you have management controls, then life is going to be much, much better. So quickly, we'll look into the differences, the broad differences. So understanding the processes and make sure that, like, we prevent fires, explosions, runaway reactions, or any kinds of process safety incidents. That is what is process safety. And a structured management system to make sure that, like, you manage the risk-based process safety management. So you're bringing in a management system. So the primary objective here in process safety is to protect people, assets, environment, and business. Whereas in process safety management, you ensure that the same objective, this objective to make sure that we protect people, is systematically achieved, maintained throughout the plant cycle by involving everybody who are part of the manufacturing life cycle or who are part of the organizational life cycle. Okay. So the focus areas: hazards, risks, consequences, safeguards, and technical integrity of process. Whereas in case of management, you'll start involving people, procedures, systems. So whenever you're talking about system, leadership, people, procedures, then PSM, that means you're essentially talking about PSM as a PSM, sorry, PSM, sorry, process safety. Yeah. So anyways, I think many of the slides will be shared to you. So process safety management itself is having various elements. OSHA talked about 14 elements. Various companies across the world have developed their own process safety management systems. Say, like, DuPont, which is a very famous company, which has developed its own PSM methodology, which is similar to OSHA, but OSHA is in fact the government federal body of US. So many of the US companies, it's actually mandatory that you have to follow. Nowadays, many companies across India also are following. Quickly, what is a success indicator? Success indicator is to have no process incidents. Whereas in case of process safety management, you need to make sure that you create a safety culture, you create learning indicators, and you need to have an effective implementation of PSM elements. Okay, so when it comes to process safety, it uses PSI, the process safety information. Again, I would like to tell you, process safety information, as I just mentioned, process safety information broadly is the information which is required for you to manage process safety. So the process safety information is broadly categorized into, or is broadly having three categories. Category 1 is the information related to materials. The category 2 is information related to your process, or which we can call as a process design basis. And the third is information related to your equipment. So you have materials. So all the information related to materials, which includes material safety data sheets. That is where you talk about the materials information. These materials are brought together. They are actually made to come in contact with each other, depending upon the kinds of processes or operations you manage. Like, in case it's a reaction, or in case the reactor, you try to bring in 2-3 reactive materials to come in contact with each other and make them react. So similarly, in case of extraction, you have different kinds of encountering of materials. So in crystallization, you have different kind of encountering of materials, where material starts coming out of a solution phase or various ways. So we're not going to get into details of that. So that information related to those processes is actually a part of the process design basis. And then these processes or operations happening inside some equipment. So you need to definitely know about the information related to equipment, whether you want to conduct this processes in stainless steel reactors, Haskell reactors, titanium reactors, or glass vessels, or what sort of pressures that your reactor equipment has to handle. All those things actually become part of the equipment design basis of the equipment information. So material information, reaction or process, design information, process information, and then the equipment information. They three broadly come under PSI, and then you use this PSI to understand hazards and design safeguards. That is how, in fact, you use PSI for process safety. Whereas in case of process safety management, you not only generate, maintain, update, validate, and in fact, you ensure that it is utilized across the organization. So that is where, again, systems management comes into play. So yeah, just I think as you can see the screen, you yourself actually can read through. But one important point is, in case of process safety, the ultimate objective is to have a safe process. And whereas in process safety management, you want to have a safe organization in total, which is capable of achieving the objective of process safety. Okay, so this is in a nutshell. In case you have any queries related to this, you can in fact write in the chat box. I will talk about it later. So anyways, again, PSM I already talked about, so I'll just skip through. This is these are the 14 elements of OSHA's PSM. So it talks about process safety information, which we just talked about. Process hazard analysis is something which most of you guys have been doing. So this fact uses process safety information. So process safety information becomes precursor for many of the elements which follow: operating procedures, the employee participation, training, the contractor training, pre-startup safety review, which is required when you are starting up new equipment for the first time, or in fact having an equipment or a process for the first time and you are starting for the first time. So how you're going to do that to make sure that you don't have any incidents or accidents, that is part of process safety. Integrity is all about how you, somebody was talking about containment. Yeah, so integrity is about like how you make sure that all the equipment and all the equipment which you are managing or which are processed, they properly hold the materials throughout the manufacturing life cycle. So many issues of your nuts and bolts actually becoming loose, your corrosion actually happening, you don't have proper preventive maintenance, your safety relief for having an issue, ruptured discs are having an issue, you are having an issue wherein the vent scrubber is not working well, where your refrigeration system is not working well. So all this actually become part of your mechanic integrity. So we don't want to get into details again, but these are elements of process safety management. One is management of change, which is a very, very crucial aspect. DuPont essentially talks about this very, very critically. Many incidents have happened across the globe because of improper MOC procedures being in place. MOC is management of change, wherein if at all you're trying to bring in a change, whether it is change in a technology, wherein you are trying to bring in a new technology, bringing a change in a facility where suddenly think it's replacement of a kind. Earlier you are having a pump. So suddenly a pump, there is a failure and pump actually got damaged. You immediately replace with a new pump and say that okay, it's a replacement of kind. Whether you have made all the changes that are necessary so that the change actually is validated in the sense, and the change doesn't in fact create a problem. In fact, if you go deep, whenever we change something, the life actually can be very miserable. I mean, that's what has been proven multiple times. We'll talk about a couple of state case studies also where MOC had been a big issue. And third thing is people. So technology, facility, and people. So that's why DuPont talks exclusively about these three MOC aspects in detail, and it is in fact very relevant also. DuPont is in fact a famous chemical company, and they had seen dark days in their own until now. It's running for many years, and so they themselves had seen many incidents, and they themselves had seen MOC is actually big issue. People also, another important thing, people also, suddenly you get new people on board and they're not trained on your process. See the kind of damage actually can be caused. Even though we feel okay, I mean, there are so many people nearby, they can, we can train them, or there are senior people also, these young guys will come and learn, or they know how to manage, because in case there is an issue, they will ask. Many times what happens is that this bringing in people is not a big issue, is what we think, but many times this is going to be a problem. So management of change for technology, management of change facilities, and management of change people, all three are very critical. Incident investigation is something which is very crucial, because you really want to make sure that incident reoccurrence doesn't happen. Emergency planning and response. So many people must be there here who are from safety department, who are from safety department. They know very well what I'm talking about. But it's all about, like, whenever you have emergency situation, how you're going to respond to that. Then we are talking about audits, safety audits, crucial. In fact, many of the companies, I'm telling you, all those companies which improved tremendously, they actually improved because of safety audits, and especially self audits. Many times what happens is that, when you're doing audits, different, huge organizations wherein, like, there are different departments. People actually conduct, people want to have this audits wherein one department goes from one department, people go from one department to another department and they try to do audits. It is proven beyond doubt that those audits work, but it is been proven that self audits actually are the best audits, where people from within the department only look into their own aspects, look into their own department aspects and resolve issues. So trade secret protection is something that OSHA talks about. So more or less, DuPont also talks about the same, more or less. But as I told you, management of change, there is in facility, technology, and people. That is something which DuPont talks about always. This is, again, I want to take it forward. This is AICHE's vertical. They also talk about PSM. So PSM is now being exclusively talked across by various organizations, being talked about. In fact, if at all you look into, many companies have their own PSM structure, and because it's very relevant, which is relevant to their own organizational structure, relevant to their own management, you definitely, you can make changes. So you can have customized approach to process safety management also, because ultimately you want to bring in management controls, you want to bring in systems, you can bring in systems the way you want to bring it. So all those people who are attending now, who are at the senior positions, who are at vice president, senior vice president level, you can actually think about how you can customize such a way that PSM works for you. This is actually the Hendricks safety pyramid. Hendricks safety pyramid says that there are so many risk behaviors actually keep happening across. We keep seeing a lot of unsafe acts happening across our organization, and then we just say, okay, I mean, we can. People just pass them. People just don't look at them seriously. Few things they look at seriously, but like for every kind of a risk behavior that is there, or unsafe fact that is there, you always can have a potential fatality at the top. So It has been proven that when you have many risk behaviors or unsafe acts, they'll convert it to near misses. Later on, those near misses only will convert to injuries, and then later on to lost workday cases, and then ultimately fatalities. So, unfortunately, we try to look at the top two of the pyramid and then decide whether we are safe or not. But we really miss out on what exactly is happening at the bottom of the pyramid. So we only look at the tip of the iceberg, we say, but there is down below so much that we need to straighten lots of things in our workplace. So much that, we see almost nothing on the top. And it's been proven beyond doubt. So when we keep on looking at unsafe acts and reduce, the better we are going to have. Okay. So I just talked about this. So our focus is understanding chemicals, their reactivity behavior, understanding reactions in detail, unit process or unit operations, and then develop design process and engineer the process to be safe on commercial scale. Ultimately, you are all from industry, you're doing your businesses. So the ultimate objective is you want to make sure that your industry is running safely. Okay, so we'll talk about a few case studies. So I'll talk about case studies and then I'll just interrupt for some time that I can hear from you. I talk about important, very famous chemical disasters which had happened, and it is important I actually talk about them. One of the worst incidents that had actually ever happened in the history of chemical industry is an incident in Oppo, Germany in 1921. That was a time when the population boom was happening across the globe. When the population boom was happening, the food crisis was there across. So people, in fact, we had to grow more plant. In the sense, we had to grow grains, rice, vegetables, and stuff. So for that, we needed fertilizers. So those were the days when people used to go all the way to Chile and pick up from the Atacama Desert the pans, sodium nitrate, which you know as chili saltpeter. So they used to get that and convert into nitric acid, and then later on convert into a lot of fertilizers. Thanks to Haber-Bosch process or Fritz-Haber process, wherein ammonia process was developed wherein nitrogen and hydrogen they react with each other to form ammonia. And once ammonia synthesis actually was developed by Faber, and it was later on engineered by Bosch, and the wonderful ammonia plant came into existence. And then later on, the downstream processes were much easier. So this is in fact an Oppo plant wherein they were preparing ammonium nitrate and ammonium sulfate. And so it was moving so fast because the fertilizer was required, nitrate deposits used to be there. So a lot of these companies used to store large quantities of ammonium nitrate and ammonium sulfate. So their thinking was, okay, ammonium nitrate in fact can be stored for a long time, and they can in fact be powdered also easily as and when required. So whenever there used to be lumping up of this ammonium nitrate, what used to do is they used to put dynamite and loosen the powder, and then actually they used to take the powders. So in one of the cases wherein they were using dynamite to loosen the powder, see, understand, ammonium nitrate, you just realize, people, just understand, nitrate or nitro compounds are dangerous. Most of this, many people must be from engineering background, and I think in this session, I think many chemists also actually must be attending, right? And many chemists are also attending. So they know very well, how dangerous nitro compounds could be. But those were the days in 1920s. Okay, it was assumed that ammonium nitrate, kuch nahi hoga, nothing will happen. So they were continuously using. But one of those cases, what happened is that there was in the process of dynamite processing, the whole of the ammonium nitrate that was there suddenly in a particular silo or in a bin which was there, it suddenly decomposed. And once the decomposition started, it resulted in fire and then later on detonation. And see what sort of destruction that happened to the whole of the facility. Overall, whatever that was ammonium nitrate, ammonium sulfate, totally got destroyed. Nearly 600 people died in this massive accident. It was one of the worst disasters that happened. Then they realized, it is not that every chemical is safe. You can't assume the chemical to be safe. So we're just talking about like wherein by the time a lot of understanding actually has there been nuclear reactions also. A lot of understanding was there on adiabatic calorimeters. Okay. Then let us talk about this a very similar incident in Texas City, Texas, which happened in 1947. Again, this was a case wherein people knew about, they learned from the Oppo incident, Oppo disaster. Here also, this was actually cargo ships near Texas City was carrying again a lot of ammonium nitrate. There was suddenly smoke coming from one of the cargo ships. So what they tried to do is they tried to choke the whole of ammonium nitrate by not having oxygen exposure. But they didn't realize that ammonium nitrate inside will decompose on its own. And it actually decomposed. And then later on got detonated, and then the whole of the detonation, once it started, there were a lot of secondary explosions, and then the whole of the fire and explosions actually spread into the Texas City itself, the port. So it entered the port. So you see the port is actually, now using the pictures, the very old picture, more than 70, nearly 80 years old picture. So wherein you see the smokes in the city itself, on the port itself. It was so damaging. And it was also again ammonium nitrate incident. So those are the times where the fertilizer was different. Ammonium nitrate, a very crucial compound, a very critical compound during those days, and even during these days. So even during these days, you don't talk about it much, but those were the days. Okay. Now this is another. Here also there are 600 fatalities. Very massive accident. One of the worst disasters ever seen. Then this is another, is a Flixborough incident. So I've been talking about management of change. I'm telling you this incident actually happened because of management of change issue only. So those were the days wherein nylon, and in nylon, you guys must be knowing, nylon is New York to London. So they wanted, DuPont wanted to develop a polymer which is so wonderful that actually can beat the earlier existing polymers. So they said, we actually have a fiber which, if you start from nylon, New York, it can cross all the way to Atlantic and reach London. So that's why New York, London, NYLON, New York, London. So for that, the process is, in fact, it's a polymerization of two compounds, hexamethylene diamine and adipic acid. Adipic acid and hexamethylene diamine, they both react, and that is the latest process. Earlier was the days when people used to use caprolactam. So at that time, one of the precursors for nylon production was cyclohexane. Cyclohexane, which is a saturated cyclic compound, it's an aliphatic, cycloaliphatic compound wherein you have C6H12, C6 is benzene. So when the whole of the benzene ring is saturated, it is C6H12, which is cyclohexane. And you guys know. So cyclohexane manufacturing was happening in Flixborough incident. So in one of the reactors, there are actually 3 reactors in series, say reactor 4, reactor 5, and reactor 6. Suddenly reactor 5, they had to replace, there was a problem. So from reactor 4 to reactor 6, they connected a pipe, a temporary pipe with bellows. So because the bends were there, the bellows were in fact taking care of the bends, and then cyclohexane was pumped. There was such a leak of cyclohexane, it was a failure because they never anticipated that kind of pressure that are going to exist when you're pumping cyclohexane from one reactor to another reactor. It resulted in cyclohexane release, which the very, very flammable material, highly flammable material. There's a massive accident, and it destroyed. It is one again. It's considered as one of the biggest disasters ever, Flixborough. It killed around 30 people, but a lot of damage. It is one of the worst disasters UK, in fact, could not take. And in fact, if you're talk to any UK fellow, he's very much ashamed of what has happened in Flixborough. It is way back around 52 years back it happened, but it's very bad and one of the well-read industrial disasters. Then the mother of all, which happened in India, Bhopal, and everybody knows about it, everybody talks about it. It's a daily story. Again, this is a combination of process safety and process safety management, especially I would say complete a PSM failure case. So in case, if at all there's one country which has to talk about PSM the highest, it has to be India. A very, very bad case. Very, one of the most unfortunate incidents ever happened in history. Anyway, I'll talk a little bit because many of the people, even though they know, I'll talk a little bit about it. It is about a compound methyl isocyanate, and methyl isocyanate reacts with water to get converted to methylamine. But the problem was not methylamine. The problem was methyl isocyanate only. When water unfortunately got dripped into the reactor and methyl isocyanate started reacting with water, heat liberation resulted in methyl isocyanate releasing from the storage unit. And we are talking about 40 tons of methyl isocyanate being there, and then nearly 25 tons of methyl isocyanate spreading across and across the whole of Bhopal city. And so methyl isocyanate, which is a low boiling liquid, boils at around 40 degrees centigrade, which is similar, which is having the similar kind of boiling point like methylene dichloride. This, in fact, came out because there were multiple failures. There was a refrigeration failure wherein you are supposed to contain methyl isocyanate itself, the temperature rise not to happen, so you are supposed to have a refrigeration system in place. And methyl isocyanate reacts with water. We know it's a highly exothermic reaction, but there's a controlled exothermic reaction wherein methyl isocyanate can react with sodium hydroxide. So there is supposed to be a vent scrubber. So methyl isocyanate, in case there is a vapor release, it has to be scrubbed off with the help of sodium hydroxide, but that also didn't happen. There was a failure there also. Methyl isocyanate escaped in the environment, and it resulted in the loss of nearly 20,000 people. And we are talking about, as we talk now today, after 42 years, even now also people are affected. One of the worst disasters actually ever to have happened, and we don't want these incidents at all. So in case people who want to look at process safety, who want to look at process safety management, I'm telling you, you just have to get into details of Bhopal disaster and then actually start working in your workplace. Then you will realize what are things what you are supposed to do and what are things you are not supposed to do. It's a very heart-rending incident. One of the worst incidents actually ever to have happened. So today we are talking about, as I told, process safety. So we will talk about process screening studies. We'll talk about normal reaction studies, adiabatic primitive studies. Then we'll talk about electrostatic hazards, and we'll talk about powder handling, and we'll talk about powder safety later on. So this is a step-by-step approach we are gonna take to make sure that we have process safety in place. Okay, I'll just cut for 2 minutes, and I just want to listen from people so that in case people have queries, we'll just address, or then we'll move forward. Yeah, any questions, or anybody wants to type or chat, or anybody's raising the arm? Anybody has queries or any questions till date? Shall I move forward? Or Shalini, are you there?
Yes, sir.
Yeah. Okay. Shall I take it forward?
Yes, sir.
Am I continuously audible?
Yes, sir.
Yeah. Ameya has a question. Yeah, Ameya, you can chat. You want to speak? Can you unmute Ameya?
Okay, sir. Let me unmute. Yes. You can talk, Amiya.
I think she's saying go ahead. Yeah. And there's PSA 2277.
Let me unmute. Okay. PSA 227. If you want to say something, you can just unmute yourself.
Is my voice clear, Sharni?
Yes, sir. Yes, sir. Your voice is clear.
Okay, so I'll move forward.
Okay.
The compounds are handled. They know pretty well which is dangerous, which is not dangerous. They know which is high flammable, which is toxic, which is highly reactive. So people know, so like butyl lithium. They know most of the people know how dangerous butyl lithium could be. Okay, sodium hydride. People know how dangerous actually it could be. And then you're talking about diazomethane. People know about what kind of dangers it can carry. And also those compounds wherein you have carbon triple bonds. People know that it can be very labile. So one of the things you need to do is whenever you are managing your chemistries, definitely try to get deeper into because you're handling hundreds of chemicals. Nowadays what happens is that various companies do various kinds of jobs. So you must be from various industries. Somebody must be pharmaceutical industry, somebody must be from chemical industry, process industry, somebody actually must be doing a lot of contract jobs, somebody must be from agricultural industry. So whenever different industries do different kinds of manage different kinds of chemistries, some are highly hazardous, some are less hazardous, but and many companies, what they do is they are on fast rotation, in the sense their life cycle itself is very small. They do contract jobs, work for 3 months, and then move on to another product, then so on and so forth. So when you are having multiple chemistries and you're managing multiple products, multiple chemistries, things actually become too complicated. If at all you want to go and deep dive and look into each and every chemical, each and every process, you suddenly find it okay. Am I unnecessarily doing too much? Those kinds of things are also there. So we'll talk about it later. But it is important to actually talk about whatever chemistry you're handling, it is important to talk about those chemicals which you're handling. So you need to know about high energy chemical groups. They're very crucial, very important. And not only as a chemist, as an engineer also, many engineers actually must be attending today. So you also need to know about these high energy chemical groups which are crucial and which are very, very important to know about, and you've got to have some awareness. So it doesn't mean that you need to know and dig deep and understand and have clarity about all the materials. I'm not saying that you need to have the material data sheets for everything. Ultimately when you're managing your processes, yes, but at the screening stage, when you are doing fundamental experiments, or when you're trying to do developmental experiments and stuff, you definitely need to have clarity about various chemical groups in those chemicals, which actually can be dangerous. So these are all high energy chemical groups. That means they're very labile. They can easily break apart, or they can react very fast. So one is these are acetylenic compounds, which are carbon triple bond compounds, and there are metal acetylides, wherein like your carbon triple bond followed by a metal. It is deadly dangerous. Then you're talking about haloacetylene derivatives, wherein like you have a carbon connected to a chlorine or a fluorine. So that is also very bad. And then you have also diazo compounds, which many of the people must have handled and what are the dangers. Then all this nitro, nitrosone, nitrite, nitrates. Whenever you are having nitro compounds, I am telling you, you can almost take it for granted that some point or other they will decompose. How badly they decompose, you can't say. For that, like, you need to do your studies. But you definitely, once you are handling nitrogen and oxygen combination compounds, I am telling you, you definitely have to have clarity about what is exactly happening when you are handling those materials. You need to get clarity, and that is very, very important. So once you see nitro compounds in your process, you definitely have to be tracking those compounds, what is happening to them. Again, I just talked about the famous Oppo incident, ammonium nitrate. It was thought it's a safe compound, but what happened? So there are certain nitro compounds which actually can be very dangerous. I mean, when you, even though you operate around 200 degrees centigrade, okay, sorry, I'm actually, yeah, few words of India coming, but yeah, I would like to tell that the people who operate around 150 degrees centigrade, who operate at 250 degrees centigrade, they find that it's safe. I mean, but still you really don't know what is going to happen. Okay. And whenever these compounds are there, like, you really don't know when impurities actually come along with those compounds, or some other in the reactions, some byproducts are released, which actually can further create problems to these compounds. You really don't know. So that's the reason why whenever you see these compounds, you definitely rise. You have to take it as a point, or you have to note it down as an important point, or you have to just highlight it so that and dig deep and find out what exactly is happening to that compound. So similarly, arene diazotides, diazoates, azo compounds. Then we are talking about metal derivatives. Then all the mercury ammonium salts, they are deadly dangerous. And whenever you are having NO, NN, or NN, NN, so whenever you are having nitrogen, multiple nitrogens, 1, 2, 3, or 4 nitrogens, then you are in fact ending up into problems. Epoxides, wherein you have COC, cyclic compounds like ethylene. When you are talking about ethylene oxides or propylene oxides or those kinds of epoxides, they are also of concern to you. You definitely look into details. And another big concerning compound for sure is your metal peroxides or peroxides. Whenever you are having OO linkages, take it for sure that you're going to have problem sometime or the other. And there are compounds, and once the peroxide forms, sometime or the other, you are going to have problems. And that too, when you are not controlling temperatures, you can be left to shoot the peroxide. Any kind of peroxide will cause some sort of problem. Okay, it is possible that it might not create a problem at the conditions which you are operating at, but beyond the temperatures which you operate at, they can really cause problems. So as you can see here, these are the high hazard, high energy chemical groups. So whenever you are handling any of these compounds in your process, you definitely have to look into those and get clarity on what is happening. See, I would like just mention. I want to talk about an important point here. Because as we keep on moving, there are certain points, or based on experience I have, or based on whatever I looked, I keep on adding certain points, and these are important, crucial points. See, there is something called a design space. Many people who are from the quality by design arena, or those who are, in fact, it is safety by design or quality by design. It's all, more or less, actually, two sides of the same coin. In fact, we're talking about regions wherein we operate. So whenever we're talking about design space, the design space is a region within which try to operate a process. such a way that your process gets the best results, whether it is in terms of product quality, product yield, or so on and so forth. So more or less what happens is that your safety also is studied in the designs, within the design space only. In the sense, I'll talk about an example wherein there is a peroxy compound which is going to decompose, which will potentially decompose at around 90 degrees centigrade. And you are operating a reaction in the range of say 40 to 50. And that is your sweet spot, or as you said, for the temperature, the design space conditions are 40 to 50. And pretty sure that nothing is going to happen to me because I'm safely operating at 40 to 50. But people have seen incidents wherein the same compound, a peroxy compound, which they were safely operating in the range of 40 to 50, because of some reasons, it went out of hand and resulted in a runaway scenario and resulted in a huge explosive situations wherein it damaged commercial scale reactors as well. So please do understand, it is not important to look at sweet spot only, at the design conditions only. You have to look beyond also. That's why what you have to do is you have to create a knowledge space, a space within which you are pretty sure that you are not going to go beyond. So definitely there is a region which is a sweet spot, a region within which you want to look at and then say this is good. But you want to go and look at the conditions which are beyond your operating conditions. And that is why we'll talk about DSC and all as we move, and in the next coming slides we'll talk about those screening studies also. But what happens is that for your reaction material, sometimes what we feel are the safe conditions, once you cross and go beyond, is it really safe? Is something which you definitely need to look into. It's a very important point I want to mention. Many problems have occurred because of that. Many incidents have occurred because of that. And people have talked about safety for many, many years. People talked about the process being safe for many, many years. But after many years of operations, people landed into these unsafe, catastrophic situations that happened. And in fact, whatever I'm talking about is a truth, which happened in many, many companies. I'm not talking about as a one incident which happened in one company. It happened in many, many companies. So please understand, it's a very crucial forward. So we were talking about the screening aspects, in the sense when you are now, say, you are working as a group. There are a group of developmental scientists who are developing the chemistry, and then there are developmental engineers, the process development engineers, or the technology development engineers or transfer engineers. You are all actually working together to develop a process, and then you wanted to discuss some chemistries and at the high level, what is the way the chemistry is going to run. And in that, you talked about materials which are being handled. So there are certain points, there are certain compounds which you felt are, quite critical, based on the high energy groups that are there, felt that some critical compounds that are there. One of the fundamental level calculations which you can actually do is oxygen balance. Even though it is not very foolproof test, it's a very fundamental test which actually can tell whether there could be a problem in your process, okay, or whether there could be a problem in your materials, okay. So you got to there's an equation for oxygen balance, which is given like this, which is minus 1600 by molecular weight of the compound into 2x plus y by 2 plus m minus z. Okay. So now let us look into what exactly is X. So X is nothing but when you have see, X is the number of atoms of carbon. So if you have CX HYOZ. So X is number of atoms of carbon, Y is number of atoms of hydrogen, and Z is number of atoms of number of atoms of oxygen. Okay, so you have 2x. So the formula is minus 1600 by molecular weight of a compound into 2x plus y by 2 plus m minus b. Now, oxygen balance, either it could be positive or negative, because minus 1600 is there here. So when you're talking about 16, it is nothing but atomic weight of oxygen. See, what exactly is the significance of oxygen balance and why we need to do this? I mean, ultimately now we are just putting an equation. It has to have some significance. The significance is pretty clear. It all talks about how much of the oxygen that is present within the molecule, or how the oxygen that is present within the molecule could be dangerous for the material or for the process. Suppose say we are talking about nitromethane, which is CH3NO2. Okay, CH3 NO2, there's nitromethane. Okay, so nitromethane has one carbon atom, 3 hydrogen atoms, and 2 oxygen atoms. So this oxygen, so once there is a deterioration situation, or when there is a decomposition situation, the oxygen which is there as part of NO2, whether it can be problematic to the molecule itself. So what happens is that even though you are not supplying any kind of oxygen from outside, you know pretty well that any of the flammable materials, like any of the hydrocarbons like cyclohexane, hexane, heptane, when there is a fire, you need to have external oxygen to make sure that the material burns. So you all pretty well know about the fire triangle. So you need to have the fuel, you need to have source of ignition, and you need to have the oxygen. Which, so fire triangle, you need to have a fuel, you need to have a source of ignition, you need to have oxygen. So if oxygen is cut off, you know that fire is not going to spread. It's a pretty much part of, which you know, and that is a fundamental reason why we try to knock one of the vertices so that the fire doesn't spread. Similarly, for an explosion, there is an explosion pentagon. We'll talk about it later. So, but when we are going to say high temperatures and all, not essentially the oxygen that is supplied from outside is a problem. The oxygen from within the molecule itself actually could be problematic to you. So oxygen balance is about like whether you have any labile molecules wherein oxygen from within the molecule itself could be damaging to you. Again, I would like to tell it is just a very indicative fast calculation approach wherein you just check it out. And if at all your oxygen balance is positive, then you have a serious concern. You need to definitely look into in detail and find out what exactly is going to happen with that molecule, because the oxygen is always there within the molecule, and tomorrow by chance any you go to extreme temperatures or conditions wherein the molecule decomposes, and once it decomposes, the oxygen atoms also are going to come out, and that itself actually will be oxidizing the compounds inside. So that is the whole meaning. So this is the formula. It's a very straightforward, simple formula. I would like you to just do a quick calculation. So can you just tell, I mean, like, So M is actually a metal number of metal atoms. So here M is 0. So there is no metal here. So it is X is carbon, Y is hydrogen, and Z is X is carbon, Y is hydrogen, and Z is oxygen. X oxygen. Sorry again. Yes. Okay, so now can quickly calculate and tell at least I want 2-3 replies. Can somebody tell what is the oxygen balance of methyl nitromethane? So here carbon C is 1. So X is 1. Yeah, very quickly wait for a couple of more answers. Wonderful. I think the answers have come. Yes, good. Ali, thanks. Giri, thanks. Ameya. Yeah, you're good. Pretty good. So you have a negative 39.34. See, so the oxygen balance is minus 39.34. So what usually the past literature says is anything which is more than minus 200. So it is minus 39. So anything which is more than minus 200, that is minus 100, minus 50, minus 39, they're all not safe. In the sense, you need to look into in detail what's happening. So maybe quickly, like if it's something you see minus 40, minus 50, you definitely there is a serious concern. The oxygen that is present within the molecule, it could play devil. Not guaranteed. Again, that's what I'm saying. This is not a foolproof test, but it is an indicative test. Tells about like the oxygen that is present with the molecule. So now you have got trinitrotoluene. Good guys. I mean, I think now wonderful. I think you have answered it right. Now let's go to TNT. So fast. You people are very fast. Very very good. We'll give a try for trinitrotoluene. So Amaya is answered. So Amaya, you can type in the chat box. So what do you feel? You feel minus 74 is a cause of concern? Wonderful. PPS, good, very fast. So Amaya, you can type. I hope you are hearing Amaya. So do you feel minus 74 is a cause of concern? Yeah. So see, you know that all these compounds, in fact, are dangerous. In fact, they're explosive materials. You go to high temperatures, they can create a havoc. And they are all less than or more than minus 200. In fact, see, we know that nitromethane is dangerous. You know that trinitropolene is also dangerous. Okay, so you're pretty clear. Okay, so yeah, ethyl hydroperoxide is also dangerous. Yes. So and they are all in fact points of concern. So what happens is that once you see an oxygen balance and once you see a slightly higher value, say preferably minus about 200, if it's something which is very low, minus in fact minus 800, minus 600, I think you don't have to really worry about. But oxygen balance gives a quick feel of how safe the molecule is. There could be some exceptions wherein you have sodium azide, where there is no oxygen at all. Then you can have a very high negative value. But these are all highly labile molecules. So there could be some exceptions. So these exceptions are due to the nature of the molecule itself, because the molecule itself is labile. When you have a weak double bond or a weak triple bond, which in fact, acetylides or acetylene compounds, even by strike of the hammer, they can get ignited. In the sense, you're talking about the labile nature of the molecules themselves. So those are the cases wherein you need to pay attention. Those are cases where you need to have special attention and look into those also. So having knowledge of chemistry will help. And these kinds of calculations also will help you to take a quick call, whether you want to go further or not. So at this stage, we are talking about screening only. See, when you started your chemistry, you really don't want to get into the details of, or you don't want to generate data for the reactions in all the reactions which you're studying. Suppose I'm just telling, you are doing a discovery, drug discovery, you're doing drug discovery studies. Forget about drug discovery studies. You're talking about, you're doing process development studies wherein the management asks you to work on, say, 20 different chemistries. And if at all you want to study all these 20 different chemistries in your equipment, reaction calorimeters or, your thermal screening units or differential scanning calorimeters, I mean, it's a waste of time, energy, and because you're still screening. So at this stage, these kinds of studies actually will be very important, because nowadays, write a program, you can just enter the molecular, so that you can actually enter the details of X, Y, Z and the molecular weight, and then it gives the oxygen balance values. So nowadays you have these Excel tools where you can do it, or you can just use a lot of AI tools also. You can just give the formula, and then you can start entering the molecule names, and then you will start getting the results. So a lot of advantages are there nowadays. So, but see, nothing is beyond experimental testing. So experimental studies are something we are going to talk about now. So I think good. I think these are the quite few examples which I want to give. Any questions on oxygen balance? I think there is one interactive question, so I will move forward because you already have answered one. So I'll just move forward. Now let us talk about, so we talked about oxygen balance. So we talked about high energy groups as the first test of screening, and the second is oxygen balance. The third is very important, chemical compatibility. See, chemical compatibility is one of the major reasons for many accidents in the process industry. I hope screen is visible for you guys. I mean, I think you are able to properly see, right? Chemical incompatibility, wherein two chemicals are there, they're incompatible. See, it's not about the reactivity, so it's not about the reaction component. Suppose say you want the reactant A and reactant B to be there, you want them to be incompatible because you want to have a reaction between A and B. So in that case, I mean, there is no point about incompatibility point. The thing is that you add so many other compounds. You add, say, a catalyst, you add a solvent, or you add a combination of solvents, and then you make up the whole of the process mass. And you expect that there is no issue of compatibility, or there is no compatibility related concern, or you say that there is always compatibility. Incompatibility is not a question, is something or you ruled out. This is based on your general knowledge. But once you deep dive, you'll realize that there are so many aspects of incompatibility which has resulted in problems. So there could be incompatibility between solvents and your key raw materials, or the key starting materials, or the key reactants. And there could be reactivity incompatibility between solvents and reagents. And also, many times what happens is that you take these materials and then try to manage an equipment, and these materials must be reacting with your equipment also. The equipment, or in the sense, there is MOC compatibility. The material of construction of the equipment is itself not compatible for the materials you are handling. So it can be arising from anywhere. So one of the important aspects when you start working on is to look into the incompatibility aspects. Is there any chance that there could be incompatibility between materials? You need to look into. And there are various support softwares. I'm telling you, even though I'm not actually going to give any demonstration today because the time is less, but I want you to guys to look into softwares. There is one free software by the name Chemical Reactivity Worksheet, which is by AICHE. It's a free software. You go and check in Google. You will be able to download it and start using it. In fact, you will be able to understand what is, and it is, in fact, it's a self-learning in the sense the program you can easily learn. You just start using it, you will come to know how to use it. And there is one more program by Cameo, which is developed by Environmental Protection Association of the United States of America. So both are US entities only. EPA's Cameo is very good because it has more features. And CRW, Chemical Reactivity Worksheet, it is also excellent. It tells about, in case you have two compounds and you are using for the first time, you can check in that. Enter in that and check whether there's a compatibility between those two compounds or not. And you have got various books also which can help in this regard. So I'm talking about Chemical Reactivity Worksheet and Cameo, which is going to talk about incompatibility between materials. And in case you wanted to understand the properties, you have got Aspen also. You have got Mixprops and Cheetah. They are also available now. You can buy them. Obviously, you have to. Aspen is quite expensive. You know that. I don't know. Many people must be using Aspen. Those people who attended this program, but there are certain programs which can be very useful to you. But Cheetah, Cameo, and Chemical Reactivity Worksheet are free softwares. Please use them. They are very helpful. I'm telling you, for those people who are doing developmental studies, and also for those people who are in fact doing PHA studies, you find these to be very relevant softwares, and they are very easy to use also. You select two compounds and check the compatibility between them, you'll realize what is exactly happening. Most of the information is taken from historic literature and all the information that is available from the World Wide Web or the worldwide information. They collect it and then put it across. So it is a very authentic information in the softwares. But you have got books also nowadays, again, because of the availability of ebooks. You have Bretherick's Handbook of Chemical Reactivity Hazards. One of the most famous books also nowadays, because people are using less books, because the e-version of Bretherick's could be very good for you. If at all you want to understand the incompatibility issues, you can get deeper into these books and understand. and you will realize that, like, there are so many aspects which you actually, you missed out in during development studies. Though those come out as actually, those come out with clarity. I'm telling you, many incidents have happened. Again, I'm telling you, small or big, in India itself or abroad itself, wherein people had managed materials, they found that they were incompatible, but when they look back into the literature, the information was there. So that means it is, in fact, a shameful aspect when you have available literature about incompatibility, but still you go ahead and use those materials. So first thing you have to do is, whenever you have materials, check the compatibility. Even though your chemistry knowledge says that they are very much compatible, nothing wrong in checking the incompatibility aspect. It's a very, very crucial aspect. I'm telling you, people take very lightly, but I'm telling you, it is not at all a light thing. I myself had seen in my own experience how dangers could occur because people didn't look at incompatibility aspects. Okay, so look at these books. Anyway, the presentation will be shared to you. Information you will get. There are various books which are available, which you can buy and use them also. Okay, and as I told you, don't miss out on downloading chemical reactivity worksheet and Cameo from the web. They are free software. You can download and use them, and they're very easy to use. Okay, so I would like to talk about solvent reagent incompatibilities. Like tetrahydrofuran has incompatibility with thionyl chloride, hydrochloric acid, chloroform, and all formyl compounds, potassium permanganate, etc. Acetone has bad incompatibility with peroxides. Ethyl acetate with sodium hydroxides, thionyl chlorides, and metals. And methanol with halogens, methyl chloride with azides, and DMF. I am telling you, this DMF, DMSO, I myself had come across, I had encountered, or had seen, wherein people had misused DMF and DMSO and ended up into problems. DMF with sodium hydroxide, DMF with halo compounds, and DMF with strong bases like sodium hydride and all, they are deadly dangerous. And they are all captured when you look into your chemical reactivity worksheet and check DMF and sodium hydride, it will tell how dangerous it is. In fact, this information is available in Brithrics also. Again, DMSO, these are all high boiling compounds, and many of times what happens is that when they try to recover, because they are all costly solvents, they go to high temperature, they recover, and at those high temperatures, you have residual amounts of these bases. You will realize that you are having serious problems. Okay, so incompatibility, again, I was just telling, incompatibility, general incompatibility has to be looked into for sure. But you have to see whether in case there are like tricky solvents or compounds wherein the literature says that they're incompatible, and you find them not to be incompatible at the conditions which you're operating, that means they can be dangerously incompatible at the temperatures beyond. You need to look into what is, are there any ways, or is there any probability of you encountering those situations wherein you have that incompatibility surfacing. So look into the literature, look into the software, get the basic information first, and then take steps. It's a very, very serious aspect. I'm telling you guys, people take it very lightly, but it is quite dangerous. Okay, so chemical reactivity worksheet, the difference, I mean, again, you just download the software. What chemical reactivity worksheet does and what Cameo does, you will get to know. I'll not go into detail. It's very easy to use. You can just download the software and start using it. It's very easy to use and very friendly. Okay. Now I'll talk about a case study. The case study is about a compound called chlorosulfonyl isocyanate. Chlorosulfonyl isocyanate. It's taken along with, so this is the compound which is say one of the starting materials along with another reactant. So it is used in a solvent, tetrahydrofuran. Now the reaction was initially, or the people were using for years together, and the CSI and THF, and the reaction used to happen at say minus 20 degrees centigrade. So never they found any problem with THF. Reaction used to happen smoothly. The product used to be obtained. People used to go to the next stage, recover the next stage product, and then they used to go for downstream processing. Never there was a problem for 15-20 years. In one off incident, what happened was that the reaction is chlorosulfonyl isocyanate was added minus 20 degrees centigrade, and then tetrahydrofuran was added to the chlorosulfonyl isocyanate was added at minus 20 degrees centigrade, kept. But the reactant B was not immediately available. So what they told was, okay, let us keep the solution on hold. But then, as it was taking more time, they said, okay, why we need to lose why need to lose the refrigeration cost, because we need to use brine. So let us actually stop brine, remove it, and let us bring it to ambient conditions. And then later on, once the raw material B was available, because of some quality issue or concern, something, the B was not taken. So they were holding it in the reactor itself. And once the reaction was brought to room temperature, what happened was that, see, there was an exotherm. And it was found that once it reaches 30 degrees centigrade, there is no stopping the reaction. The mass itself will go to 172 degrees centigrade. Adiabatic temperature rise is the additional temperature rise that happens when the process mass, when a process mass is taken to a certain temperature, the reaction happens. What is additional temperature rise that actually is going to happen in adiabatic conditions? 140. So 30 degrees centigrade was the temperature, plus 140, 172 degrees centigrade is a temperature which ultimately the process mass would go up to. You're talking about tetrahydrofuran, a solvent which is going to boil at 66 degrees centigrade. So just imagine, just because you're operating at minus 20 and for years together you are finding it perfectly safe, just because one raw material was not available at that juncture, you were just holding the mass, and you just actually thought of saving some money for the company. Why to waste, the temperature? Why to waste money because you are using brine? So let us cut off brine, put cooling tower water, and then hold it for some time till I add. Until again, I have a situation wherein I can actually add the raw material B. And then you saw that the smoke was coming, the whole mass was actually like boiling, and then there is a potential catastrophic incident. So these things are very, very crucial. So what happens is that we assume that our experimentals also you have done, laboratory studies also revealed that there's not a problem, but this is at the conditions which you are operating at, okay? And but so with all due respect, with all the experiments you have done and with all the care you have taken, you have completed the process also running, but suddenly there is a change that happens, and people want to bring in a change for good only, for doing something good for the company only, but the process which is developed around 15 years back, it is running now, and then suddenly they ended up into a new kind of a problem which they never envisaged also that would ever happen. So what you're talking about? So friends, I'm telling you, it's very, very crucial to look into the incompatibility issues very, very carefully. And that is the reason why I was talking about design space and knowledge space. Yes, there is a space, the region within which you definitely look into the safety aspects, but you have to go beyond and also look into whenever you feel that there are some criticalities. Okay, so and that too, whenever you are using some materials which can be like labile, isocyanates. You know that there could be a problem. So you always want to operate at -20. Like especially what happens is that all those people who work with beta lactams chemistry, who worked on penicillins, who worked on cephalosporins and all, they all know that they have to operate around -50, -60, those kinds of temperatures. But in case because of some issues, the cooling failure had happened, and if at all this process masses came to a conditions which you generally don't operate at, what is going to happen? So that kind of information you definitely have to be aware of. That kind of information you need to have. That kind of testing you need to do. And that also, I will not say that you have to do for every case. It is your call. You have to look into, you have to do your own brainstorming within your team and then take calls. But I'm saying, don't be myopic, be a little bit broad-minded, look into your process scenarios 360 degrees. That's why when you are actually doing real PHA, see, that is the reason why PHA becomes a very crucial study. Whenever you are doing process of analysis, the PHA team will start questioning by what happens when you go beyond, and that triggers off you to generate more information which is more relevant. So process safety information generation is not just one track; it is very holistic. So many times what happens is that your further process element, when you are doing studies or when you are conducting studies which are as part of other PSM elements, it will trigger off further PSI generation scenarios also, which makes you to in fact generate all the relevant information. Ultimately what you want actually safe process, you want safety. But safety for what? Not just safety for this process, and also at the conditions which you're operating at, and not essentially you want to operate at the conditions which were given in the operating procedures for the process to be successful. It doesn't mean that you will always be operating at those conditions only. Because there could be some control failure scenarios, or could there situations wherein you can just go astray because of lack of controls or because of various reasons. So you look into those potential scenarios and then accordingly generate information for yourself. Okay, clear? And then later on, once this was seen, they realized, and then they changed the solvent acetonitrile. Then they did tests, went up to very high temperatures, around even 150, 200 degrees centigrade. They found that the compatibility was very much there. Then they switched over from one solvent to another solvent. So they removed THF because later on they realized that the THF was converting into peroxides and further creating a problem. And once peroxide formation was there, at high temperatures, the peroxides were exploding. That was the reason. So then the people switch over to acetonitrile. So incompatibility aspects, very crucial, very important to look into. So we are going to screening of process. Any questions till date, you can write in the chat box. I can answer because we are going to the next section. Any questions till now, friends? Very good. So let's actually go into screening now. Say you now you have a process with you, and now you want to take the process to the next level, wherein hopefully you want to commercialize the process. So once you are about to commercialize the process, you want to look into your process masks. So your process mask goes through various stages, right? First of all, it goes through reaction, and later on it will go through a series of unit operations, and then you'll get the finished product. So you have starting materials. So when you want to screen your starting materials, you screen your essentially raw materials and solvents and stuff. You want to screen your intermediates, which are produced at various stages, and obviously the final product. And you are getting various you are getting, in fact, materials, or you are getting some mixture of solvents, or mother liquor, or some filtrate, or some organic masses, which are essentially having some solvent or any kind of unreacted reactant, or so on and so forth, which you want to recover those compounds from. So you have these organic layers or process masses from which you want to recover your solvents or other, in fact, raw materials also. So those ones also you need to take it for screening. Then reaction masses, process masses at various stages, whether it is for various unit operations or even for your reaction masses. And then mother liquor, I already talked about it, because whatever mother liquor you get after filtration, you want to distill off again and recover solvents or some materials from that also. And then when you are distilling, one of the biggest problems you have in industry is when you're doing recovery, when you're doing distillation, an improper distillation or improper recovery procedure can really sabotage your complete plant, or it can destroy your plant because you didn't study in detail. So what you need to do is, once you are ready to go for commercialization, it's important to study various process masses which you feel are very, very crucial for you. And nothing better than your DSC studies. So even though there are many tools which have come up, differential scanning calorimeter arguably is the best screening tool that is available for screening studies as far as process safety studies are concerned. Differential scanning calorimeter gives essentially the heat of a reaction or any kind of exothermic or endothermic heat that is liberated when you are taking the material from one temperature to another temperature. So DSC essentially has two components. One is the sample cell, another is a reference cell. You don't have anything in the reference cell. You don't have any material in the reference cell. It's a blank cell. And in the sample cell, you have material. You keep on taking both reference cell and you keep on heating both reference cell and sample cell. At a ramp rate, which is actually at some degree centigrade per minute or per second or whatever. And then you go from one particular temperature to another temperature. As you are ramping up, if any thermal event happens or any heat event happens or any kind of exothermic heat or endothermic heat, either exothermic heat is released or there is a heat absorption from the material, you will come to know, because the temperature is forcibly maintained as per the ramping equation, and the heat either is absorbed or released and grabbed by the instrument. So the instrument measures that heat and tells what happens. So in case of a DSC, as you see here, you go from a temperature, you start from a temperature, so preferably at ambient conditions at around 30-40 degrees centigrade, and you go till 200 degrees centigrade to 50 degrees centigrade and see what is a thermal event that is occurring. Right? So once you see this thermal event, you will try to see how bad is the thermal event, and then accordingly decide what is happening to that process. So I was just telling, suppose say you are having a test of intermediate compound, and just you plain intermediate compound which is purified, you wanted to test, and you saw that when you keep on heating the intermediate compound, you found that the compound is in its purest form also, it is decomposing and it is giving a huge exothermic thermal event, indicating that the compound is decomposing, but not only it is decomposing, it is liberating a lot of heat. So this in fact tells about the property of that particular compound. So depending upon your process requirements, you need to do these studies. And I'm not saying that you have to do all the studies. It is your call how you have to perform these studies, because ultimately your objective is to screen them thoroughly, understand what are the hidden dangers within the process. Clear? So in case of DSC also, you just, and there are DSCs which are exclusively for safety purposes. You know, DSC is used for various other applications. DSC is used for polymorph applications also. They want to understand the glass transition temperature. They're used for polymer applications. They use for property studies of actually materials. But people actually nowadays have realized, or many people are using it for safety purposes. Even though it is for 80% for quality purposes, 20% for safety purposes, but I'm telling you, DSC has an immense use as a safety tool and as a safety screening tool. DSC is definitely a screening tool. It has definitely a lot of disadvantages, but it has got wonderful advantages as well. Because there is no great screening tool like DSC, because you are not only testing various materials, but in fact test across temperature ranges. So that is the reason why, and as you know, in reactivity hazards or reaction hazards, temperature and pressure are the two crucial aspects. And in case, and concentrations also to a certain extent, but concentrations are something which you control, because when you are doing process development activities, you don't increase the concentrations of reagents just like that. But temperature and pressure are, even though you want to control at certain range, or you want to have certain range within which you want to operate or you want to control it, there is a possibility because of it, you go beyond. So you go beyond the design space. And that is the reason why you have to create a knowledge space and understand what is happening. So that is the reason why when you are doing these studies, you will come to know what is happening. And you will not only come to know what is happening for your only pure products, or not only your intermediates or finished products. You can do tests for your reaction masses, and you can test for mother liquor also. Tomorrow you know that, like, the mother liquor, which is actually around 7,000 to 8,000 liters lying with you, and management says that, we have to cut down the cost. There is around 23% solvent in it. You try to recover the solvent. I'm giving a huge column, with 20 theoretical stages, and you try to recover that, because there is going to be a cost saving of around 15 rupees or 20 rupees per kg. Then you just embark on it, and then you end up saying that you are supposed to carry out a distillation at 150 degrees centigrade, and you saw a thermal event at around 70 degrees centigrade itself, which is so catastrophic. Who will give this information? This information will come from your DSC. Later on, you can do further studies, a different story, but this is the initial screening tool you need to use. Okay. Yeah. Everybody clear? So till now? So just I would be happy if at all you can give a thumbs up. Yeah, good. Nice. Thanks a lot. Yeah. So in this graph, you can see, there is a typical DSC curve, how it looks like. There is a glass transition temperature, as you see, wherein the crystalline mass is getting converted into an amorphous mass. And then later on, there's a crystallization event for which there is exothermic energy release. Then as you keep on heating, there's a melting that happens. Yeah, okay. There's a crystallization event, which in fact the crystallinity is lost, and the material is getting converted to amorphous compound, and that is the where you will see the exothermic heat. So this is heat of crystallization. When you again take amorphous material and you reverse back and actually again grab the crystals, you'll get a similar heat. And then later on you start melting it. Melting is always an exothermic event because you have to give heat from outside, and so it's endothermic event. So this is how you will get. So you look into this data, collect this data, and then calculate what is the total heat of melting. So in fact, DSC, if at all it's done accurately, you can calculate the heat of crystallization, heat of melting. So those kinds of properties you can in fact generate, and in fact it's used also. DSC is used also for generating that kind of data. Now I'll go to the next slide. Is it visible for you? The whole it's all visible. Shalini, can I zoom it up?
Yes, sir, but this picture is not visible like this. What it is written now, it is not visible.
Yeah, so how can I zoom it up? Can I zoom it up?
No, sir, I don't think so. There is any option?
Okay,
yes, sir, you can.
I will just go and just zoom it up a bit. Okay. Yeah. Is it visible now?
Yes.
Is it visible now?
It is visible, but that values are not clear. But we can say it is okay.
No, what I'm doing is I just wanted to zoom in, and now I zoomed in. You're able to see that?
Yes, we are able to see.
Okay.
The value that is written, it is blurred, not clear. So anyway, it is okay.
Okay. Yeah, that's okay. Now, friends, as you see here, there is a thermal event that is happening. Okay. So as we move forward, this is in fact a DSC graph for a typical process. As we move forward, see there is a temperature at 128 degrees centigrade. There is a thermal event which is happening. So suppose say you are carrying out a reaction, and you have taken all the materials which are required for a process to happen. You have mixed everything, and then the reaction will happen at say 75-80 degrees centigrade. You know that, or you know that around 80-90 degrees centigrade is the temperature of the reaction happens. And then you put all the materials together, and then you started heating. You're doing just DSC test, and you understood that when you once you go, so at 128 degrees centigrade, the thermal event happening. And you know that at around 195 degrees centigrade, thermal event stopped happening. And between these two temperatures, there is a temperature, there is in fact there is a heat that is released. And whatever that is heat that is released is given here in a DSC. DSC gives a value in joule per gram. Okay. DSC gives values in joule per gram. Joules are the amount of heat that is released in joules. And per unit gram is the total mass, suppose whatever you have taken the DSC crucible, that weight is taken. And the total heat released divided by that sample weight is what it shows as this. Here you see, I don't know, sorry. I'm zooming in here on my screen. I hope I don't. Okay, here you see the total heat released is 649 joule per gram. Okay. Now I have a small, I want to give you some information. Few are engineers, few are chemists, but I would like to tell that whenever you are having any thermal event, say you are having mass M, and you are having a thermal event wherein some heat that is liberated, which is delta H. That delta H is equal to mass of the material that is taken into specific heat of the material that is there into delta T. That is the total temperature rise that happens when you have any kind of a thermal event. So delta H is equal to mCp delta T. And this delta T, delta T is the temperature rise that is going to happen, is nothing but delta H by mCp. Okay. And this delta H by mCp, when I say, it includes delta H by m by Cp. And delta H by m is nothing but your joule per gram, which is already given by your DSC. So that joule per gram value, if at all you divide by just Cp value, it will tell how bad your reaction is gonna be, or how bad your process, or how bad your that particular process mass is going to be. That clarity you will get. Okay, here I'll tell you. I'll go to the. This is the graph I will have to go, and here you'll want to see. Are you able to see the screen? Okay, here you have a heat delta H value of 551.636. Okay, and the temperature of onset is 105 degrees centigrade. The temperature of onset is 105 degrees centigrade. 105 degrees centigrade is the point at which the thermal event started happening. Okay, so I'll put in the chat box. I told delta H is equal to m into Cp into delta T. Okay, delta T. This is what it is. So 551 is, so delta H by m is what DSC gives. Okay, that means I hope you are all looking at the chat box. Delta H by m is what DSC gives. So this is in joule per gram. Okay, now this delta H by M, so let us actually call it as H by M, this is equal to now Cp delta T. So if at all you want to calculate delta T, it is nothing but H by M by Cp. I want you to look at the chat box. So now I've shown you, guys. I mean, now I have shown you. This is the okay. Shalini, are you able to see the heat value here, Shalini?
Yes, sir.
So 551 is your delta H. Okay. Now, friends, if at all I tell that Cp value is 2.2 or 2, Cp value is simply 2. Okay. So if at all I say Cp is equal to 2, then you are saying, yeah, so delta T, yeah, already somebody said 275, wonderful. So 275 degrees centigrade is a temperature rise, it happens. So you have an onset of 105 plus 275, that means you are going to 380 degrees centigrade. That means this thermal event, if at all you go to 105 degrees centigrade, the whole mass from 105 on itself will go to 380 without any external intervention. 105 you take to, then that's it. The thermal event itself will trigger off heat release. It will further heat up the mass. Then further actual temperature will rise. And again, then the rate of reaction at the high temperature will keep on increasing till the complete thermal event is completed. And by that time, the temperature would go up to 380 degrees centigrade. So, if you are operating, say, you want to operate, say, at 80 degrees centigrade, and by mistake you went to 105, what is going to happen? So I want you to write in the chat box. What do you feel for this part? I shown the thermal incident. Yeah. So as I told you, yeah, there's a question from Ramakrishna. Mr. Ramakrishna, M is already embedded into it. So when you said joule per gram, that means delta H by M is taken already by the instrument. So instrument, what it does is, because when you are in a sample crucible in a DSC, when you put a sample, when you put material, the material weight is taken by the instrument. So it calculates delta H and it will divide by M, because M is to be inserted, the instrument itself takes, and it will give delta H by M value. So M doesn't arise. Clear, Mr. Ramakrishna? Yeah. Yes, Anish, Abhishek Giri is telling it will go to runaway. Yeah, wonderful. Macklin D'Souza, yes, it is actually, yeah, telling, yeah. So, yeah, temperature, Dilip Patel, temperature will rise to 275, but because the event is happening at 105, you have to add 275 to 105. Okay. So that means it will go to 380. Clear? So the final temperature will be 180. Yeah, Mr. Jitendra, wonderful. So it will go to runaway. In the sense, so what happens is that you will not be able to, not in a position to control. So these kinds of screening studies will help to figure out what exactly is happening. So DSC studies will not only tell exactly the temperature at which onset happens, it will also tell about how much is going to be the impact that will be there once the onset happens, and it will also tell what is actually potential damage you can have. So DSC more or less gives a pretty clear picture. Okay. Yes, Ranjit Kumar, you're very right. In fact, insufficient cooling in case, but there is actually certain aspects which I have to talk. I have to talk about when I talked about adiabatic calorimetry. I will give more details because this is a little bit complicated. Ranjit Kumar, yes, insufficient cooling, very good point, very valid point. Yeah. So subsequent pressure rise also can lead to an explosion. Yes, pretty clear, pretty good. Wonderful, friends. So nice. Yeah. Now I'll give one more example. I think some people have asked. See, there is one again data. This is a nitro compound here, and it's the process mass testing that's being done here. So the reaction usually happens at around say 50-60 degrees centigrade, but the post reaction, whatever the mass that was there, what was taken, so it was post reaction mixture was taken and it's subjected to DSC testing. And at around 128 degrees centigrade, those people who are seeing it a little bit blurred, I will give you a little bit clarity. So, but I'm this I zoomed in. I don't know whether you are able to see my screen. But in case you are not able to see the screen, I can tell you there is a thermal event for a nitro compound reaction mixture wherein the thermal event is getting initiated at 128 degrees centigrade. So the T initiation, T in is 128. Okay. And the delta H value is 649. Okay. And I want you to take a specific heat of 2. Okay. Now let us do this exercise. Yeah. So I think lots of, sorry. So delta H, I'll again type, is 649. T in is the initial, that is where the temperature, that is a temperature at which a thermal event is getting triggered off. It is 128 degree. Okay, 128 degrees centigrade. Okay, and then Cp is 2. Delta H is 649. Sorry, I missed the unit. G per J. Okay, joule per gram. I put in the chat box. So can you tell me, friends, what is going to be the temperature rise? Already Abhishek Giri is telling 324 degrees centigrade is the temperature rise. So delta T, which is adiabatic, we can solve delta T adiabatic is 324. So can you tell me what is the final temperature T find? Because the temperature at which it is reaction is triggered is 324, the decomposition is triggered is 128. What is the final temperature, Abhishek Giri? It is 128 plus 324. Wonderful. 452 degrees centigrade is the temperature you would go up to. Yeah. To be precise, 324.5 ppm. Yes, wonderful. Okay. Yes. Excellent. I think, yeah, you are in track. Everybody got it. So I tell you, so this is the process mass wherein, like, you are having a reaction mixture. You are operating at around 80 degrees centigrade. And you have managed the reaction very well. And if at all that 80 degrees centigrade, if you didn't manage well, just imagine. And by mistake, it reached 128 degrees centigrade. I will tell again why it can happen. And once there is a decomposition which is getting triggered off, it will give a heat release of 649 joules per gram. That means the 324 degree temperature rise. So 128 plus 328, 452 degrees centigrade is the final temperature it reach up to. See the kind of potential catastrophic situation you will have. This is what DSC tells you. DSC tells about what are the thermal events that are there and how bad they are and how dangerous actually they could be in case that event arises. So that is the reason why I am telling, when you are having, again I go back, you are having various process masses. So look into all the process steps and see which process step essentially needs a screening testing because you are doing certain operations. Suppose a reaction mass, here point number 4, is going for further concentration, wherein you want to, many times what happens is the process mass is little dilute, and the diluted mass you want to concentrate. So in the concentration you start evaporating, in the sense you start removing the solvent, and as you concentrate, temperature rises, and suddenly, reaction happened at an 80 only. You carefully taken the reaction temperature to be at 80, 85. You have excellent controls. Then you, after the reaction is over, you did a HPLC test, found that a product is pakka forming, no raw material, the reaction has gone to completion. Then you take it for concentration, and you are concentrating, usually concentrate using hot water and applying vacuum. 95, 90 degrees centigrade is what is the maximum temperature you go up to. But suddenly one day what happened is that they said, okay, by vacuum is not there, somehow you still have to complete the batch, you concentrate. Then you said, okay, hot water is not sufficient for me, I'll apply steam. Then you started applying steam. And when you start applying steam, the temperature will keep on increasing because there is no vacuum, the temperature will further build up. And if once it reaches 128, what happens? The concentration is still happening. What happens? This is what would happen. This is what would happen. Okay. So, pretty clear, friends. You give a thumbs up. I mean, I hope you understood my point. I mean, how important it is to study DSC. I hope you are pretty clear. So there is one small exercise, I think pretty clear. So you guys are pretty clear. See, in this graph, you see there is one event which is happening, is ending at 195, because DSC, in fact, the heat is absorbed within the DSC only, and the temperature keeps on rising. So you will not see that adiabatic temperature rise as you see it in commercial scale reactors and all, because DSC, what it does is, DSC, the temperature will be constant only. In the sense, suppose it goes from 128, slowly it goes at a temperature rise of 10 degrees centigrade per minute, and it go to 195. It go at the same rate. You will never see the reference temperature, sample cell, and the reference cell will keep on moving at the same temperature rate. But whatever the heat that is liberated or absorbed is grabbed by the instrument. So then one more thing, as you see, when you keep on going to 198 and it further goes, there's one more thermal event which happens at 300 degrees centigrade. So what happened to our case? The first event itself is so bad, the temperature will go up to 450 degrees centigrade. So in that process, the second event also would occur. So whenever, in case of the real damaging scenarios on a commercial operating facility, the first onset itself will trigger off. Once the first onset itself, there is actually thermal event which is triggered. The thermal event heat release is so high that will keep on raising the temperature of the mass, and the second thermal event also will happen and it will further add to the first thermal event. Both will get added up, and further damage. Okay. So there is one more graph similar. See, there is one thermal event which is happening at 141 degrees centigrade, and the heat release is 324 joule per gram, and then again there is the thermal event stopped at 250. But as we move forward, there's one more thermal event which happened at 251 degrees centigrade. And there is actually heat release of 334 joule per gram. And again, the thermal event ended up at 320. So I have one question now. I mean, I have, you guys are really doing well. So I have a very interesting question. So first event, say I'm just giving, the first event is 330 joule per gram. Second event is 340 joule per gram. Now, T onset for the first event is say 150 degrees. Second onset, T onset, second event is 250 degrees centigrade. Okay, I put in the chat box, friends. Now you please look into it and tell what exactly is happening. The CP value is 2. Okay. When the first event happens, what is the temperature rise? And what is the second, when the second event happens, what is the temperature rise? And is the second event is happening much before the first event ended or not? Clear? Can you give me? Can you keep on answering the chat box? If at all you are clear, I think get the clarity so that it's easy for everybody to actually move forward, because it's a very, very important point we need to know. It's important point for your screening studies. You've got to know about it. Okay. Wonderful. I think Abhishek Giri, you wonderful. You're right on the button. Wonderful answer. You've given, yes, wonderful. B. Srinivasa Rao. Yeah. Good, very good. So first event itself is going to end at 305 degrees centigrade, but the second onset itself is 250. So the second onset gets initiated. So this before actually the first event ended. Yes. Great. I think pretty clear. I think wonderful. Yeah. I mean, I think you all have clarity. I hope anybody having questions, you please raise in chat box. I think it's pretty clear to everybody. I think it looks like people are answering the right way. No, I think Chirag Patel is the same Chirag Patel from Torrent Pharma, because I know you. If at all you are Chirag Patel, Torrent Pharma, Chirag Patel. Yes. When TT24 values actually can't be. Oh, hi Chirag. I know you, Chirag. Deepak Nitrite, Chirag. Wonderful. Okay. No, TT24 from DSC, it's not possible. We definitely have to talk about that, and we definitely have to talk about when we talk about adiabatic calorimeter. So DSC, it is not possible. Yes. Can we test heterogeneous reaction mass in gold crucible? This is from Hetero team. The answer is yes. But the problem, these are the limitations in a DSC. I will talk about them in the coming slides. DSC has major issues. The real DSC's major issues are like there is no mixing. When you take a sample and put it in a crucible, you're just going to heat it. So in case of a conventional reactor system, you will have proper mixing taking place. But in case of a DSC, there is no mixing. So you are having heat, the heating of the crucible takes place, but if at all you look into the microscopic level, what is the heating rate of the bottom layer of the mass in the DSC crucible? What is the heating rate of the mass which is on the slightly top layer of the DSC crucible? They're all of a concern. And because mixing is not happening, whether the heterogeneous sample is properly mixed or not, whether the reaction mass itself, whatever you inserted, is proper or not, those kinds of questions will definitely come. So the hetero team, your question is very valid. Heterogeneous reaction masses, there is a cause of concern, but I can tell you, whatever data you are going to get, it can be used as screening information. In case if you have to thoroughly mix the process much as possible outside only, because you can't mix inside, because you are taking very few. I mean, you are taking milligram level of samples inside DSC. So when you are taking such small quantities, mixing at that level is not possible. So you have to prepare a representative mixed sample outside, and from that representative sample, you have to make small quantities. So make sure that you mixing you do outside, and then you give that ensure that whatever heterogeneous mixture you are taking inside as a sample for DSC is as accurate as possible, in the sense it represents the real process mass. So the representative sample you prepare outside is very crucial. You prepare it well, and then you take the sample inside the DSC crucible. Okay, there is a challenge, but I am telling you, people have done wonderfully well, and they have proven that they get wonderful results using heterogeneous masses also. Fairly accurate, at least you get 90% accuracy. It makes you take calls. See, I'll tell you, DSC is not a tool wherein you make conclusions. DSC, and you will not go ahead and design. DSC helps, it's a screening tool. But many times what happens is that people have taken calls using DSC and operated processes for years together safely. So when you are having only DSC, suppose like you're talking about an adiabatic calorimeter, like accelerating rate calorimeter, which is ARC, and many tools like Phytech, ARC, and all, which are adiabatic calorimeters in the market. They're advanced tools wherein you get a lot of information. These instruments give wonderful information, but these instruments are very costly, so not every company can afford. So people use DSC studies only and use that information for at least deciding about the safe operating limits, safe temperature limits at which the process has to be operated at. So those kinds of things, whether you can do from DSC, the answer is, if at all you want to have accuracy, the answer is no. But in case I create proper representative samples and then I do proper DSC testing, is the data acceptable? The answer is yes. Is the data reasonably good enough for me to do further studies? The answer is yes. Is it okay for me to, in fact, do scale-up studies? The answer is also yes. But only thing is that you have to make sure that you take proper representative samples. So there are ifs and buts, but people are using DSC data. People have used DSC data for years together. I'm telling you, many big companies also have used DSC data and are operating commercial reactors or commercial process for years together. Okay. So DSC again, see, I'll tell you again, DSC is a very crucial tool because it tells about what are the safe operating ranges for your process mass or for your process. Earlier, DSC was used only for testing a finished product or an intermediate. But now people have realized that DSC can be used for various applications. Tomorrow, for concentration purposes, for solvent recovery purposes, you want to know the information. So for that, like once you know that you are conducting certain operations, you have to sit down and decide for what are the masses for which you have to do testing. Then you go ahead and do testing, and then check it out whether the particular condition is safe for you or not. Okay, and whether you can actually get reasonably accurate values. As I told you, if you create proper representative samples and then test, you will get fairly accurate results. The only thing is that, as I told you, DSC, there is no mixing inside the cup. And second important point is, obviously it is not adiabatic system. So the delta H values are reasonably accurate, so you can take them. But whether it is going to be a foolproof solution for you, the answer is no. Chirag Patel was asking Deepak Nitrite. He was talking about TD24. I will talk about it later because it's a slightly advanced topic. I will talk about it. And once you go and test an adiabatic calorimeter, it will give accurately what exactly is going to happen for decomposition reactions. Okay. Any questions you have? Arvind from Bangalore, can we get 5 factor? The answer is no. You need to have a adiabatic calorimeter for that. So that I will also tell mostly I think post lunch. So what is the answer for temperature rise in the first and second unit? Yeah, I think the first temperature rise is 315 degrees centigrade. And then the second is plus 170, 485 degrees centigrade. So actually, I want to make it clear for those people who didn't understand. I want to tell you the first onset, the first onset was at 100. As I told you, the first onset was at around 150 degrees centigrade, and the delta T adiabatic was 165. So 150 plus 165. The temperature, once the onset happens from 150, it will go to 315. But the second onset happens at 250 degrees centigrade. That means as the temperature is rising continuously because of the exothermic heat, the second onset also would happen. In the sense, you will have now both heats, the heat event for the first event and the heat event for corresponding to the second event, both will be happening in the sense that both the decomposition reactions will be happening. And finally, the temperature would go up to 485 degrees centigrade. Okay. Amol Vishwas, I hope you are clear. Okay, sir, is the condition is adiabatic only or replicable for isothermal reactions? No. See, I am telling you, when you are doing any process, you go to a certain temperature at which a thermal event happens. When a thermal event happens, there is a heat release, and we are talking about the heat of reaction of the thermal event is, say that depending upon exothermicity or endothermicity, we will come to know how much is the damage it can cause or what is the temperature rise that will happen because of the event. And we are assuming that the whole of the mass is adiabatic in nature. If at all something is not adiabatic, what is adiabatic condition? There is no either temperature loss nor temperature gain. So the heat mass is neither losing heat, or the process mass or the reactor is neither losing heat nor gaining heat. Once you are heating the temperature, the process mass, at one particular point, suddenly the heat event happens, and the steam is at say at 130 degrees centigrade. Heat event happened at say 165 degrees centigrade. As I told, 150 degrees centigrade is the first thermal event. At 150 degrees centigrade, steam is available. At 150, a thermal event had happened, means the thermal event will take the mass to 350 degrees centigrade. But the reactor will start losing some heat in the middle. If it loses some heat, what happens because of the loss of heat? The temperature of the mass will not go up to 350. It might go only up to 300. It might go only up to 290. So, but 315 is a worst case scenario. And we know that the first thermal event, once it happens, it will potentially take the mass to 315. But the second onset is happening at 250. So before the first event gets completed, the second event also happens and takes the temperature further. So this is what we are actually trying to say. Okay. So isothermal reaction, since you want to conduct a process at isothermal condition only. Suppose you want to concentrate. I was talking about an example. There is a process mass. You want to evaporate further. So you wanted to operate at around 120. You took at 120 degrees centigrade and operating 120 only. But a thermal event happens. Then the decomposition will start taking up the reaction forward. In the sense, the whole process mass temperature is rising. Now, not because of external heat. Now, steam is not playing a role. Only the mass itself will start getting heated up. And then the reactor, if the reactor works as an adiabatic reactor, where there is no heat loss or heat gain, the temperature will go so much that it will go to 315 degrees centigrade. And before 315 degrees centigrade, second event also will happen. Clear? I hope it's pretty clear. Right? Okay? Clear, friends? I'll quickly conclude here because we have to break for lunch. So now this is about DSC. Any questions about DSC? Because we are moving slow, we have to move fast because we started it. And I have to talk about normal reactions and adiabatic calorimeter. I will definitely try to make it a little bit faster in the post-lunch session. For the good of everybody. So but it's important point I stopped because DSC is so crucial. Because why I stopped why I talked about DSC for so long is because I'm telling you, as we move forward, there are many tools which only I think nowadays it's possible that around 60% of the industries are having. But there are 30-40% of the industries, or even, as I say, if at all you look into small, big, micro companies, nearly 80% of the companies don't have these advanced tools. So it doesn't mean that companies which have advanced tools are only safe, or they are the people who are now having that luxury of being safe. No. If at all you use your existing tools appropriately, you can still make your processes safer. That is why I talked about DSC, a very important screening tool, and it's a very crucial tool also. Okay. Now let us talk about the adiabatic reaction, advanced reaction screening tools. There are tools like Foscase. This is one tool, which is Foscase ARSST. Which is the advanced reactive screening tool, and another is TSU, thermal screening unit. This is from Foskey, and this is from Hazard Evaluation Laboratory, HCL UK based company. What it does is what these two tools do is I'll just see. I hope you are seeing this. So when you keep on increasing the oven temperature is given in blue color. Then you will have a sample pressure which is given in black color and sample temperature which is given in red color. So, and one particular temperature you see suddenly, irrespective of whether you are having oven temperature or not, the temperature is just rising. That means this is where a thermal event is happening. And at the same temperature, around that temperature, you see there's a pressure built up also. That means there is some release, mostly of gas, because the pressure will not get released, or pressure will not get increased. unless until there is some gas or some vapor which is going beyond its boiling point. So, and predominantly gas only, because once the decomposition happens, there's a gas only emanation that happens. I'm just giving all practical possibilities and see how bad it is. So these are the values which you get in thermal screening unit. So thermal screening unit, what it does is, it will give practical values. So because it will not give any heat value, it will keep on tracking temperature and pressure, and it will tell how the temperature rise is happening, how pressure rise is happening, and it will also give the differential dP by dt and dt by dt. It will give the rate of rise of temperature, rise of rise of temperature, and the rate of rise of pressure. At what rate pressure is rising, at what rate temperature is rising. And here, so temperature rising is happening linearly. It's almost uniform. And suddenly it is picking up. Here also pressure rise is happening, picking up. That means there is a huge thermal event that is happening. So this is slightly advanced screening tool because it exactly tells what happens. And also it tells what is the kind of pressure that is going to rise. With DSC, you will not be able to know. In case of thermal screening unit, it will be able to tell what is the temperature it will go up to, and what is the pressure also it will go up to. So this clarity you will get. And this helps you to decide what you have to do with your process. So these screening tools will tell, again, these are the screening tools which are going to tell what is a safe zone and what is unsafe zone. I take quickly 2-3 minutes, which is important. I can actually share you the slides. These are all thumb rules, but anyway, important thumb rules. If at all your area is greater than 500 joule per gram, you're talking about 324, 330 and all. Any exothermic event, once you see, you can expect that there is an explosive event which will potentially occur. 500 joule per gram, if at all you divide by 2, specific heat of 2, 250 degree temperature rise usually has to be explosive in nature. If area is greater than 100 joule per gram, it's divided by 2, that means the temperature rise will be 50. You are having definitely a highly exothermic event. Okay. Now, whenever exothermic event happens at, say, beyond 200 degrees centigrade, better to operate with a 100-degree rule. Even though I'm telling about these people who are not having advanced tools like ARC and all, can use this 100-degree rule, they say, but it is reasonably safe. Because once you are not having any thermal event, 100-degree question, if at all you give, it is going to be pretty safe. So the safe operate, suppose say you are having an exothermic event at 220 degrees centigrade. Tell your team not to go beyond 120 degrees centigrade. Suppose you want to carry out concentration of a mass. You saw that when you are concentrating a reaction mass, exothermic event happens at 220 degrees centigrade. It is an exclusive event. So 220 minus 100 is 120. 120 is the safe maximum temperature you can operate at. Even in the worst case scenario, you will never go beyond 160, 170. So 120 is actually the safe maximum temperature. Even if at all exothermic event were to occur at around 160, 170 also, you are still safe. Okay. So in case an exothermic event happens above 150 degrees centigrade, but below 200 degrees centigrade, you don't definitely go beyond 100. Okay. So these are the thumb rules which you can use. And in case you are using only DSC and DSC is only screening tool available, these are reasonably safe thumb rules. Okay. Isothermal testing also is possible to be done using DSC. Okay, isothermal testing, why you have to do is, I'm telling you, in case you want to carry out, say, distillation operations, or you want to do concentration operations, or you want to do post-reaction some operations, or you want to do reaction operations also. Suppose you want to carry out a reaction at around 80 degrees centigrade. you take the process mass to 110 degrees centigrade and operate at isothermal conditions and check whether you are having any thermal event. So 30 degrees centigrade beyond operating temperatures, you check and see if at all isothermic event is happening. And at isothermal conditions, in the sense, I'll tell you again, I want to give clarity. I'll just stop for a while and tell you. Suppose say you are having a reaction which is conducted at 80 degrees centigrade. You completed the reaction, HPLC testing is done, product is through, and the reaction mass is through, product is formed, raw reactant is not there. You took the whole mass, kept it with you, and now later on you have to take for concentration purposes. You are evaporating. For that you are using steam, and you are using steam at around 120 degrees centigrade. Okay, and you know that the concentration happens very well in laboratory. Okay, and for that you are using 120 degrees steam, 120 degrees centigrade steam. The process mass is around 110 degree. Now 120 degrees centigrade is the temperature at which you are operating. So you add another 30 degrees centigrade. So take to 150 degrees centigrade and do your DSC testing at 150 degrees centigrade and check whether any event happens, because that temperature you added up another 30 degrees centigrade and you are trying to replicate that concentration experiment in a DSC and see if at all any issue is there, and if at all you don't have any issues, you are good to go. So you can go ahead and do your testing. You can go ahead and do your commercial operating experiments, because you have already done an isothermal testing experiment. Okay. In case you wanted to have, you are working on a very thin line and you are having very narrow gaps, you are having dangers associated with your process, then I am telling you, don't go for DSC. You have to go for ARC. Okay, fine. So I think we'll stop here and then we'll come back and then we'll have a lot to learn. I'm pretty worried whether we'll be able to complete, but we'll go ahead. Okay, what if the onset is 110, 120 degrees centigrade above my operating temperature, but delta H is 13,000 joule per gram? Is it safe to operate with the DSC data, or I have to go for additional testing? What if the onset is 110 to 120 degrees centigrade above my operating temperature? No, here the question is by Yatish Kohli. The answer is, the question is from Yatish Kohli. I'm trying to quickly answer what you're telling. What you are questioning, Yatish Kohli, you are saying delta H is 1300 joule per gram. When it is 1300 joule per gram, I am telling you, you are having a potential explosive scenario. That means it's deadly dangerous for you. But onset is at 110 to 120 degrees centigrade above the operating temperature. Suppose the operating temperature is 80 and your onset is 200. At 200 degrees centigrade, you are having an explosive event. Whether 80 itself is safe or not is a question mark. The question is, what you need to do is, if at all you are ending up DSC, my suggestion is, for such a scenario where you are having a very badly explosive scenario, nothing wrong in going for adiabatic calorimeter, because if at all you do adiabatic calorimetry studies, it's foolproof. Done. I am telling you, adiabatic calorimetry is in case you do adiabatic calorimetry, that's it. It's a full stop. Because it gives all the data for you to take process forward. Okay, with full confidence. Adiabatic calorimeter data is something once you have, you can blindly take that data and go ahead. Unless until you have change in concentration, change in mass, and all adiabatic calorimetric data, you can just go ahead with. But in case you want to do with DSC, if you ask me whether you can go ahead with DAC data which says that 110-20 degrees centigrade above the onset or above the operating temperature, I would say yes. Aram say you can go ahead because it will not give such a bad data. So the real issue why people are having problems with DSC is they don't give a representative sample to DSC testing people, and that is where the issue happens. And you come back and say that around 60 degrees centigrade is a question you told I can use, but I have used the 60 degree question, but still I had an explosion. That means, did you give a representative sample? All those questions will come in. So when you have dangerous, potentially explosive scenarios, let us not take risk. Let us go for foolproof techniques. But 120 degrees centigrade is a very good question. You can just go ahead and take it forward. Okay, 120 degrees centigrade is a reasonably good cushion. You can around go ahead with Yatish Pali. See, ideally speaking, thermal conversion is, in fact, has to be chemical conversion only. So, ideally speaking, thermal conversion and chemical conversion are same. So, if you take the area under the curve and then suppose say the total heat of reaction is calculated by from the reaction from start to end, you will have heat data starting from 0 and then increasing and then later on becoming 0. So the area under the curve, so Q is the rate of heat release, T is the time. So Q and T curve you will have integral of Q dt, that is the area under the curve of Q and T will give the total heat of reaction. Suppose say for 50% total heat liberated, it takes 50% of the area of the curve divided by the total area and tells what time exactly that particular 50% reached. So this is what is thermal conversion. In fact, thermal conversion is proportional to chemical conversion. But the problem is, in realistic scenarios, there will be multiple reactions that will be happening. Along with your wanted chemical reaction, there are so many other simultaneously thermal events happening, small, big, and all. So because of that, your thermal conversion or the thermal values or the heat rate values are combination of multiple thermal events that are parallelly happening, including side reactions. So that is where like your thermal conversion actually fails to give the best replica of chemical conversion. But to a certain extent, you definitely can use. Analytical method you can use for understanding chemical conversions, and then you can juxtapose. You will see that there is generally around 70 to 80% overlap happening. In fact, realistically speaking, also you will have overlap. So that way, it is fine. So in case you are having complex chemistry, in case you wanted to generate kinetic data, or you developed a kinetic model, and you want to use that kinetic model for predicting the reaction rate constants, and if at all thermal conversion data is enough for you to get the rate constants from the kinetic model, nothing wrong in using your thermal conversion value for generating the rate kinetic equations. Nothing wrong. So you can go ahead. In fact, we have done a lot of experiments in the past. So at least I myself had worked on at least 10 to 12 cases wherein we developed our own kinetic models, used thermal conversion data to generate reaction rate kinetics information for those very complex chemical process wherein even getting analytical data is difficult. Suppose say there are reactions wherein you can't send for HPLC or you don't have either analytical techniques, then obviously it's very difficult then. So there are certain complex cases, they will have certain complex cases wherein chemical analytical data is not easily available. Then we can definitely use thermal conversion for getting rate constants and developing our own kinetic models. Get the constants using those models. I hope I'm clear. I think just we are waiting for the stroke of 215 because we told the time is 215 for people to rejoin. So we are just giving some time. So in case you are having any other questions, so please post so that I can answer. First of all, I'll ask Nathan Kishore. Heat losses in TSU are there. TSU is not an adiabatic system, so TSU, that's why the screening tool, it will tell what is actually going to be the temperature at, or what is the, at what temperature you suddenly see a sudden temperature rise or a pressure rise, indicating that there's a decomposition. So once you see an indicative, once you have feel of when the temperature, at what temperature there is going to be a pressure increase or a potential onset, that is the information which you can use further to design your process. So it's a screening tool and it is a pretty good tool, and because you will be able to understand exactly where the onset is happening, and also you will be able to understand what is the kind of pressure increase that's going to happen, pressure rise that will happen, how much pressure and how much temperature. So, but it is not an adiabatic system, so obviously you will have heat losses. Now, FTA and FMEA. See, FTA and FMEA are not in this scope because FTA is fault-tree analysis and FMEA is failure mode effects analysis. So this is basically a kind of a process analysis tool wherein like you try to talk about a failure mode or an event to have occurred, and then you will try to find out what are the causes for the particular event to occur, and then you will try to apply some safeguards such a way that the event doesn't occur. So it is a PHA tool. So for performing FMEA or FTA, you might need some safety data. So we are talking about, obviously, see, even though PHA can be embedded as a part of process safety, but we are trying to find out step-by-step procedures such a way that you will get relevant information for yourself, so that you will be able to develop safe process. That's the whole objective of we meeting today. Generally, Arvind Anisetti, we have to test DSC, or we have to do DSC testing at a rate of 10 degrees centigrade per minute. That is the usual rate we suggest for screening samples. So 10 degrees centigrade per minute sampling is very good. Testing is very good. So that means if at all you want to go from ambient conditions, say 30 to 300 degrees centigrade, that is 270 degree jump, you require a 10 degrees centigrade per minute, means it is half an hour. So a DSC test of half an hour is a very good way of doing your screening. And so 10 degrees centigrade per minute is what is the usual testing method. And if at all you do it 5 degrees centigrade per minute, you are going to have slightly better accuracy, in the sense the onset will be much better. And if at all you do it 1 degree centigrade per minute, it is still better. So first of all, you just screen it at 10 degrees centigrade per minute, see if at all any thermal event is there. And in case a thermal event is there, then you can go for a slower rate of testing, so that you can consolidate on the onsets. So don't waste your time, because DSC comes at a price. So better do it 10 degree per minute, no problems, because you're saving time. You can test more samples. And then later on, once you see thermal event and once you see that there is a problem, then you can go for lower temperature rates, in the sense of 4 degree per minute or 3 degree per minute or 2 degree per minute. Pi factor in CSU is something which is better we don't talk. Not because pi. We don't have to talk about pi factor when you're talking about TSU, because TSU is just a screening tool. It is better we don't talk. And in fact, there are certain things which, even if at all we try to do with DSC and TSU, and then try to predict. Actually, one question Chirag Patel was asking in the morning, whether he can predict TD24 using DSC. See, there are certain tools which actually tell that you can predict, but I'm telling you they are not foolproof. So that is the reason why it is better we don't talk about that. Okay, Shalini?
Sir?
Yeah, you are there. Shall we start?
Yes, sir, we can start.
Yeah. So I think everybody is there, and I was trying to answer a few questions. Yeah, some question again. Arvind Anishet is asking, does testing rate depending upon type of crucible? The answer is no. See, generally for safety purposes, people are using gold seals. Okay. So there are serious concerns. If at all you use a conventional DSC, many times what happens is that the cell damage and all happens. People are having some concerns, but there are certain safety DSCs which Mettler sells, and even I think even many other companies are selling. So which is for safety purposes. So it's okay, but DSC actually some DSC which is used by analytical people also is used for safety purposes, and I know how extensively we have also used in the past. Yeah, but general their crucibles with gold seals are good enough. Does testing rate depends upon type of crucible? Yeah, the answer is no, as I said. What are the safe temperature margins for different heating rates? No. See, first of all, there is nothing called safe temperature margins. First of all, you actually do it at 10 degrees centigrade per minute, and then you get a thermal event, and you do not look at onset. Then if at all you feel it is very alarming for you and it is almost nearer to your operating conditions, that is where you have to do at a slightly lower temperature rate. And if at all the lower rate onset and 10 degrees centigrade onset, there is a difference of only 2-3 degrees centigrade or 5 degrees. It doesn't matter much, right? So there's nothing to worry that. Okay, so this is what I just wanted to give a clarity. Okay. So guys, we'll answer further questions later. Thanks again for joining. I hope the first session was informative for you and useful for you. Many people are operating or managing reactions or processes which are hazardous in nature, and even with all the awareness, people are figuring out how best, in fact, they can sorry. So people are sorry, I just slipped. I'm sorry, I slipped. Actually, I just slipped a point or two. I'm just sorry. I think there is a miss here. DSC, many of the companies are managing with differential scanning calorimeters and differential scanning calorimeter data, because the information for using advanced tools are not there, or they don't have actually they don't have accessibility to these high-end instruments sometimes. So they manage with DSC data, and they use the DSC data. In fact, DSC data can be effectively used also, or the screening tools can be effectively utilized and used. The reality is you have to look into your process and find out where exactly you need to do the testing. When I talked about screening tools right from the morning, I was talking about oxygen balance, I was talking about compatibility issues, I was talking about chemical compatibility aspects, I was talking about DAC testing. Before that, I was talking about high hazard groups and all. So all these are all actually can be used in hierarchical way, in a way that you use the right tool at the right time. And when I told you, I think you are intelligent enough to understand, like, what tool has to be used at what time, and which tool you have to invoke at what time. I mean, is it required that you have to do DSC testing for all the process materials? The answer is no. You have to use them at the right time, at the right place. And in case you are having some concerns, then only you have to go to the advanced tools. So many a time what happens is that you do testing, nothing happens. If you do a DSC testing at 10 degrees centigrade per minute, there's no thermal event at all. And then later on you take the sample, I have my own doubts, if at all you do it around 1 degree centigrade per minute, and you also don't see any thermal event. And then later on again, you try to do adiabatic calorimetry. That means you are unnecessarily wasting your time. So we got to be smartly managing. But please understand, there is no compromise for safety. So once you start seeing something alarming for you, you definitely act very fast. Now the next stage, so we have talked about screening. The next stage is about normal reactions. See, that is the most crucial part, okay? The most crucial part we are reaching is how to manage normal reactions. Normal reactions instance, what exactly happens, or what exactly is the chemistry you're desiring to have? The chemistry you're desiring to have, in the sense you want to conduct reactions wherein your material A reacts with material B to get product C, and you want to have that reaction to take place. So with all with your what do you call smart planning, intelligence, a lot of analysis, a lot of research, and a lot of experimentation, you come up with an optimized process. So I know that you are using your own tools to optimize. And then you say that I have to carry out the reaction at so and so temperature, at so and so concentration, and all the conditions and parameters which actually are required for the process to happen. Now, once this process happens, what exactly is happening to your reaction? What sort of heat release that's happening in a real normal process is very crucial to be understood. You will be surprised to know that, okay, this understanding, first of all, I'll tell you, this understanding happens through a tool called reaction calorimeter. It is one of the most wonderful inventions that have happened, at least for process industry, in the last 60-70 years. See, we are talking about nuclear reactors, we are talking about atomic bombs, we are talking about hydrogen bombs, we are talking about understanding nuclear fission, nuclear fusion, and all the processes about nuclear chemistry. Okay, but you will be surprised to know and understand that the reaction calorimeter came into existence after 1960s. And the first reaction calorimeter in its commercial form came into existence in 1980. So you are talking about a tool which is very, very new. Maybe just surprised, right? Many people are surprised. I mean, it's a surprising aspect. So reaction calorimeter is this wonderful tool that makes you understand in real time what exactly is happening to your process, to your normal process. Because ultimately what you want to conduct is a normal process. See, we are talking about screening, we are talking about what are the hazards, we are talking about thermal events, we are talking about the dangers associated. But all in all, what you really want is the process to happen well. The chemistry which you design for the process has to happen beautifully, has to work wonderfully well. So, but that understanding of chemistry, I think you might be doing in the background through analytical tools and all. But what is happening to the process on the thermal front is understood using reaction calorimeters. Okay. So the applications of reaction calorimeter are multifold. Once you do reaction calorimetry, you can get hazard data, hazard evaluation, you can do hazard evaluation, you can do process design, you can have information related to reactions or basic transport. You can have process simulation and scale up, scale down data. You can do process optimization using reaction calorimeter, and you can generate material data as well. A lot of information can be acquired using reaction calorimeter. And if at all you use it effectively, it is one of the best tools you can actually ever have for process industries. An amazing tool which not only helps your process to be safer, but it also helps your process to be better optimized. Okay. So what I will do is I just before going into details of reaction calorimeter, I will quickly show you a video. It's worth watching this video, even though it's going to take 20 minutes of my time, 20 minutes, because we are running out of time. I'll quickly show you the video. Sorry.
At midnight, December 2nd, 1984, the worst industrial accident in history at a U.S.-owned pesticide manufacturing plant in Bhopal, India.
It was a reactive chemical accident. Methyl isocyanate is highly reactive with water.
Dennis Hendershot is an industry consultant in chemical process safety and has toured the now abandoned Bhopal accident site.
Water got into the storage tank somehow. Water reacted with the methyl isocyanate, causing the release, which killed thousands of people.
Thousands more died in the aftermath of Bhopal, and tens of thousands continue to suffer today. But Bhopal also brought about change.
Bhopal totally changed the understanding of potential process safety hazards in the chemical industry.
Bhopal spurred Congress to require new OSHA and EPA regulations covering chemical process safety. And Congress established the CSB to independently investigate chemical accidents.
There have been many positive changes in chemical industry process safety since 1984, when the Bhopal nightmare occurred. But the CSB has found that accidents involving reactive chemicals still occur all too frequently and often with tragic results. This video focuses on 4 major accidents investigated by the CSB. Accidents that demonstrate what happens when reactions run out of control, resulting in fires, explosions, and toxic releases that cause death, injury, and environmental damage.
Such an incident unfolded on the morning of January 31st, 2006, when a vapor cloud exploded at the Synthron acrylic polymer manufacturing plant in Morganton, North Carolina. The blast killed 1 worker and injured 14 others. It destroyed the facility and damaged nearby structures. At Synthron, a seemingly minor increase in the size of a production batch led to a catastrophic explosion. It was a tragic example of what happens when process changes are not managed carefully. Synthron manufactured acrylic polymer coating additives in batches using a 1,500-gallon reactor located inside a production building. The company had produced the polymers for years without serious incident, typically using a two-step process. In the first step, operators would partially fill the reactor with acrylic monomer and solvent, warm the vessel with steam, and then initiate and run the reaction for up to several hours. Later, in a second step, operators would gradually pump in the remaining acrylic monomer and continue the reaction until the vessel was nearly full of product. Both steps of the reaction generated heat, causing the solvent to boil. An overhead heat exchanger condensed the hot solvent vapors and sent cooler liquid back to the reactor, keeping the temperature and the reaction under control. Shortly before the accident, Synthron received an order for an acrylic product that was 12% larger than the standard batch size. Rather than fulfilling the order by making two smaller batches, managers decided to make a single larger batch and to add all of the extra acrylic monomer during the first step of the process. But this was a critical mistake. Adding the extra monomer all at once more than doubled the heat released by the reaction. The heat exchanger could not condense the vapor quickly enough, and the temperature and pressure inside the vessel began to rise uncontrollably in a runaway reaction. The pressure caused the gasket on the hatch to fail, releasing flammable solvent vapor into the building. Employees heard a loud hissing sound, saw the escaping vapor, and fled the building. 4 workers gathered outside a doorway, where they were joined by the plant superintendent and the plant manager. One of the operators went back inside the building in an attempt to send emergency cooling water to the reactor. But it was too late. The operator returned to his companions outside. Seconds later, the solvent vapor in the building exploded. A worker who had remained inside the lower level of the plant was fatally burned, and 14 others were injured. The building was destroyed. The Synthron accident underscores the need for well-rehearsed evacuation plans. Furthermore, it's critically important for companies to carefully review the effects of making even small changes to reactive process conditions.
Anytime you are rearranging molecules, you have reactive chemistry, and the potential for reactive chemicals accident is possible. Dr. Daniel Krell is a chemical engineering professor and process safety expert. If you don't mix the raw materials properly, if you add them in the wrong order, if you add the wrong materials into your process, you will lose control of the mass. In 2002, the CSB completed a comprehensive study of reactive chemical hazards, issuing key safety recommendations to OSHA and the EPA, as well as trade and industry groups. A number of the recommendations have yet to be adopted. The report identified 167 serious accidents involving uncontrolled chemical reactions in the United States over 2 decades, causing 108 deaths and hundreds of millions of dollars in property damage. More than half involve substances not covered under current federal process safety regulations. Between 2002 and 2007, the CSB investigated 10 additional serious reactive accidents and identified many others that caused deaths, injuries, evacuations, or property damage. Just because this initial screening method says you probably don't have a clearly identifiable reaction hazard, that doesn't mean that reaction hazard doesn't exist. And you probably need to look into your chemicals and their properties and their reactive nature a lot more thoroughly than you think you need to.
Reactive incidents can occur even when plant personnel are unaware that chemical reactions are taking place. That's what happened at an Augusta, Georgia plastics manufacturing plant in 2001. On March 13, 2001, 3 maintenance workers at the BP Amoco Polymers plant were killed while they were preparing to clean out a tank that held waste plastic. BP Amoco made high-performance nylon by pumping raw materials through a heated reactor and then using an extruder to form the hot plastic into solid pellets. During the first 50 minutes of startup, plastic considered to be unusable was diverted away from the extruder to a 750-gallon waste tank. Steam and gases escaped through a vent in the waste tank, preventing any accumulation of pressure inside. The contents of the tank were allowed to cool down over a period of hours. Workers then opened the cover to remove the waste plastic. On the afternoon before the accident, operators began to start up the process. But there was a mechanical failure in the extruder. While the operators tried unsuccessfully to fix the extruder, the hot plastic continued flowing into the waste tank for an unusually long time. Supervisors eventually aborted the startup, but by then, the waste tank had already overfilled with molten plastic. The excess plastic clogged the vent line and the emergency pressure relief line. With the lines and pressure gauge now sealed off, workers would have no reliable way of determining whether the tank was under pressure. As the outside of the waste tank gradually cooled, a hard plastic layer several inches thick formed around the inside surface of the tank. But closer to the center, the plastic still remained hot and molten. Unknown to workers, a slow decomposition reaction was occurring inside the molten plastic. Over a period of hours, the hot plastic molecules were breaking down, forming gas bubbles and causing a dangerous buildup of pressure. Just after 2 a.m., 12 hours after the startup attempt, 3 night shift workers approached the waste tank to clean it out. The workers began to unbolt the cover of the tank. After they had removed half the bolts, the extreme pressure blew the 1,750-pound cover off the tank with explosive force and ejected hot plastic over a wide area. The waste tank recoiled backward, breaking hot oil pipes and creating a vapor cloud, which ignited 6 minutes later. 2 of the maintenance workers were killed instantly when the tank cover blew off. The third was pronounced dead on arrival at a hospital. This accident shows how even slow chemical reactions that don't produce any heat can still be hazardous. In this instance, company researchers knew that molten plastic could react to produce gas, but that information was not sufficiently incorporated in the design of the process or communicated to workers.
I think that is one of the main issues. And it's not so much that nobody was aware of that information, but rather that the people who were actually operating the system didn't have the information or didn't have access to it. That somebody somewhere, even within the same organization, had that. So I think is education and awareness. It was not an explosion. So, was a victim of a reactive chemical accident at Morton International in 1998 in Paterson, New Jersey. He and other survivors spoke about the human impact of such accidents at a CSB public hearing on reactive hazards in 2002.
I hope this would help not the United States, but the whole, the people who care, get inside the chemical and
You remember when how I got out of that area? If my coming here today should save one life or stop somebody else from going through the nightmare I have been living, then it's worth coming here and going through the pain of living it again. Thank you.
The CSB's 2002 study found that over 90% of serious reactive chemical accidents involve hazards that have already been described in the publicly available literature. The board recommended that, to better understand reactive hazards in their processes, companies should consult multiple sources of information and conduct specialized testing if necessary. Collecting adequate safety information and data is especially important when scaling up a reactive process.
On April 12, 2004, the MFG chemical plant in Dalton, Georgia, experienced a runaway chemical reaction. It caused the release of highly toxic vapors into a residential community. The CSB determined that the accident occurred because MFG did not safely scale up a chemical reaction from the laboratory to a large production vessel. MFG was contracted to manufacture 35,000 pounds of a plastics additive called trialocyanurate, or TAC. The company produced 3 trial batches of TAC by reacting aloe alcohol and cyanuric chloride inside a small 30-gallon test reactor. In the first 2 tests, operators controlled the exothermic a heat-producing reaction by adding one of the raw materials in small portions. In the third test, all of the chemicals and a catalyst were combined in the test reactor at one time, which was the procedure that MFG later decided to use when scaling up to full production. This third test produced significant heat, but the water cooling jacket around the small vessel was able to keep the temperature low and control the reaction. However, MFG did not realize that compared to the small test reactor, it would be far more difficult to control the temperature in the 4,000-gallon production vessel. The surface area to volume ratio was much lower in the production vessel than in the test reactor. Starting the production process for the first time, operators loaded the large vessel with all of the cyanuric chloride powder and the catalyst. They then added all of the alcohol and began mixing the chemicals. To control the temperature, MFG had rented a portable chiller and connected it to the cooling jacket on the vessel. But as soon as all of the raw materials were combined, the reaction began producing heat faster than the cooling system could remove it. The temperature increased uncontrollably, and with all of the raw materials already in the vessel, nothing could be done to control the reaction. The pressure inside the reactor climbed rapidly as the mixture heated. Suddenly, a gasket blew out, releasing toxic allo-alcohol and allo-chloride vapors into the atmosphere. About 10 seconds later, the emergency pressure relief rupture disc burst open, releasing more vapor. Unable to slow the reaction or contain the release, the operators were forced to evacuate to a safe location upwind. The toxic vapors quickly spread into the residential neighborhood east of the facility. Authorities ordered the evacuation of more than 200 families, but the town had not trained or equipped its emergency responders for such an accident. 154 people had to be decontaminated, including 15 police and ambulance personnel. This accident emphasizes the need for emergency responders to be fully prepared for a toxic chemical release. The CSB found the company could have prevented the accident by better understanding the chemical process and knowing how to prevent a runaway reaction.
You don't want to be learning about chemical reactions in a 5,000-gallon vessel. You want to learn about it in a small vessel in the laboratory and understand what's going on so that by the time you get to the large manufacturing vessel, you already know those things. You don't want to get surprises on a large scale. A large 20,000-gallon reactor will run away a lot faster than a 1-gallon reactor that you're using in a laboratory. And somehow human nature is to believe that larger is slower. And in the case of reactive chemicals, a larger chemical reactor will actually run away a lot faster than a smaller chemical reactor.
Chemical reactions where high temperatures cause decomposition can produce powerful explosions. Few people realize how much destructive energy can be released, as in the following accident at a Mississippi chemical plant. On October 13, 2002, an explosion tore apart a 145-foot distillation tower at the First Chemical Corporation in Pascagoula. 3 distillation towers at the facility separated and purified mononitrotoluene, or MNT, which is used in the manufacture of dyes and agricultural chemicals. The entire facility was shut down for routine maintenance. Plant operators decided to leave 1,200 gallons of MNT inside one tower during the shutdown. This would be safe at normal temperatures where MNT is stable. The heating was shut down on the 2 reboilers by closing the steam supply valves. But unknown to operators, these valves were corroded and worn. Steam leaked into both reboilers over a number of days, heating up the MNT, causing it to break down and become unstable. On the morning of the accident, the temperature inside the tower reached 450 degrees Fahrenheit. A dangerous runaway reaction began, rapidly forming gas and suddenly building up pressure inside the tower. The tower began to rumble, and employees saw material venting quickly from a breach high in the tower. A short time later, the tower ruptured. The violent explosion propelled the top 35 feet of the tower well beyond the plant site. Another piece of the tower sailed 500 feet and hit a storage tank of MNT, setting it ablaze. A 6-ton piece of the tower sidewall flew 1,100 feet and came to rest just 50 feet from a 250,000 barrel crude oil storage tank. A piece of shrapnel nearly hit a 500,000 pound tank of toxic anhydrous ammonia. Metal packing covered in flaming chemical residue ejected from the tower and rained down across the facility and neighboring plants. The explosion knocked down 3 operators who had taken shelter just inside the control room door.
As the CSB found in its 2002 study, and in 10 subsequent investigations, reactive accidents can have serious and tragic results. To prevent these accidents, companies should identify and thoroughly evaluate reactive hazards in their processes. Appropriate emergency pressure relief systems and other design safeguards need to be in place. Companies should also develop effective operating procedures and training programs, and carefully manage any changes to existing processes. Finally, facilities need to plan for possible accidents, including evacuation drills and emergency response exercises.
The most important thing to managing reactive chemistry hazards is that you have to have a thorough and complete understanding of your chemistry under design conditions and also under all foreseeable abnormal conditions. The main message I have is that we cannot avoid reactive chemical hazards. However, chemical plant accidents involving reactive hazards are unacceptable. The technology and the management systems do exist to produce these products safely.
Much progress has been made in chemical process safety since the Bhopal accident in 1984, but deaths and injuries continue to occur from uncontrolled chemical reactions, and significant gaps remain in federal regulations and industry programs to control reactive hazards. It's time to redouble our efforts to prevent these tragedies. Thank you for watching the CSB safety video.
For more information about the reactive hazard,
Hi. So I hope you looked at the video and then you had a feel of what exactly happens, for process industry. And in all the cases, you had seen that, there were some mistakes which actually happened, but they all happened because of reactive hazards. But there were cases wherein people were ignorant or people were not figuring out what to do. So once this ignorance is there, it is pretty dangerous. You saw a case wherein people, in fact, were testing in a small laboratory reactor, and then ultimately they had gone to a commercial reactor and ended up having a catastrophic incident. So these are, in fact, nowadays becoming more and more unacceptable. You have got the right tools now to understand the reactive hazards. We have got not only the, in a sense, we have got experimental tools to get realistic values. We really don't have to assume things now. We can do proper experiments, get realistic data, use the realistic data to make sure that we design safe processes. And also we are having a lot of support tools in the form of softwares, which are piling up a lot of information from across the world, from across the history, to make sure that the life becomes easier. So you really, and in case you want to know about past, or you want to know about historical facts or the past incidents, you can get a lot of clarity, a lot of information from the web. So things have become wonderfully better. If somebody is saying, this particular accident has happened or this incident had happened because we tried our best and we did whatever we could do, but still it happened, then that means there is something which you are doing wrong. You have all the, as I told you, you have got all the tools in the world. You only have to make sure that you cover all the bases properly. You ensure that you leave no stone unturned. And if you do that appropriately, I'm sure that you're going to do wonders for yourself. Basically, having a safe process plant or a safe plant is ultimately going to be a success, right? And it is actually a fun. It is a celebration because we want to make sure that like we're on safe process. Okay, just imagine like one odd incident once it happens. The pain is going to be there for years, even for decades also. I was working in one factory, I was working in one organization, and just around a few months before I joined a company, in that company, there was a massive accident which happened. It was very unfortunate. People never wanted to have that incident, obviously. Like there was some there's ignorance, whatever you can say. And that accident resulted in the loss of 3 people. And one person was a young chemical engineering graduate who was just like fresh out of the college, maybe 1 year old. His body fell apart and actually was flying as pieces. His torso was found somewhere. One leg was found somewhere. It was a very bad incident. And in the scars of that accident are being talked right now, even after say, I would say 25, 20, 23, 24 years. Even now also people talk about that ghastly incident. So if you go back and actually check whether we could have prevented, the answer is yes. So many times what happens is that, we really don't look deeper and we really miss so many points. World is now having all the capability to make sure that we don't miss, we can create foolproof solutions. We have got all the right tools. Only thing is that you have to crave for it, you have to fight for it. When you're working in industry, you're working for organizations, or you're working as consulting companies, or you're running your own company, please do understand, you spending some time, energy and resources will save a lot of your money, and it will save you from many other aspects which anyway you can imagine. Okay, so please make sure that those ignorance aspects are dispelled off. You have all the tools, as I told again. If at all you use the information appropriately, you can get complete clarity, and you can make life of yourself and the world around much better. Okay, let's actually talk about the reaction calorimeter principle. As I told you, reaction calorimeter, the first reaction calorimeter came into the world in 1960s. Ciba, which is the specialty chemical company, was having a lot of reaction-related problems, and they were having so many reaction hazards that they were somehow wanted to overcome with a company which can fabricate or come up with a tool which is useful for them. So they have tied up with Mettler Toledo. So both are Swiss companies. So the first origin of a reaction calorimeter happened in fact in Switzerland. And then later on, rest is history. Then a lot of other tools also have come. So many other companies actually started fabricating or coming with reaction calorimeters. So simple reaction calorimeter, the basic principle of reaction calorimeter, I'll tell you. It works on the principles of heat flow. The reaction calorimeters are all heat flow calorimeters, predominantly heat flow calorimeters. What are heat flow calorimeters? Whenever heat is liberated in a reactor, heat flows from the reactor to the jacket. So jacket sucks the heat. So heat, suppose say that is QR is the heat of reaction. And whatever heat that is liberated from the reactor, within the reactor, from the reaction, if at all it has to be sucked by the jacket, you know the heat flow equation, which is nothing but Q flow being equal to UA into delta T, that is the reactor temperature minus jacket temperature. U is the overall heat transfer coefficient, A is area. Okay, so the unit of this is watt. U is the heat transfer coefficient. The unit of it is watt per meter square per Kelvin into meter square into Kelvin. So the whole unit of Q is watts. That is power. That is a heat rate. Joule per second. That's what comes. Okay. So I'll quickly go through it. In a typical heat flow calorimeter, you will have various other kinds of losses and the other kinds of heat, that is the heat components that are available. So what we try to say is the reaction heat total, whatever it gets emanated from the reactor, it's a combination of heat flow, that is the heat that is coming out to the jacket. Another is whatever heat that is coming out from the reaction is accumulated within the reactor itself by the reactor components. In case you are dosing any reagent, the dosing reagent also will grab up some heat that is liberated from the reaction.